Okay. Sorry. So now it should be live. And then do I have to like share my screen?
Whatever it says in the directions.
I sort of ventured into joining Twitter, and I was like, no, I can't take it. I'm not mad enough to do it.
I'm just not. It's still not showing up on the website.
Okay.
How do you get like 3,000 dollars? I don't really know. Yes, you're right. That's what you use it. I use that deck time to maintain tact. That's why I play across. Why do so I don't lose my mind? But, you know, some of the energy. Just a heat engine. Just convert No, it's not faculty track. But it does you. So our track one is very starters, basic science.
They have you on the first AV show.
Yes.
Okay.
I'm just gonna put this. So what's the problem right now? It's just not showing up.
It's not showing up. Wait, I probably need this.
Yeah, no, I talked about it.
I haven't shared my. Do I need to share my screen for it to?
No, it should just show up.
Okay.
If we go to the, let me go to the YouTube. Is it showing up on the YouTube? I can check it.
Okay.
No, yeah, I put in the application.
Should be able to sign in.
Okay.
Oh, is this Rachel's
I
computer?
don't worry too much about it.
Yes.
Danielle, exciting day. Good to see you again. Yeah.
Okay,
How's it feeling? Good, I guess. It's exciting.
so it's just not, that the issue is that it's just not showing up?
Yeah, on the website.
Yeah.
Can you bring up the like actual script that you?
Like the website. Okay. This is what I have.
So this room is technically 285 capacity.
I mean, it has it shown here. So it's just not. So this is like a website thing. We can find one list of this.
We can put a link in. Okay.
Yeah, it was the same. I sat down this time it leads up to the early afternoon. That's because
Well, this is the one, so it's
right, yeah.
Yeah.
Which allowed us to have a voice session. That was really good.
Oh, maybe this is the problem.
Pushback.
So this is what it. This is the actual like YouTube page. Is just showing her screen share, but it's just not showing up on the website. Okay, and you did the event, copy the event. Yeah.
Yeah.
And I don't know if she has up what she did. Like.
Yeah.
Yeah.
Sorry. Yeah. This.
Yeah, that looks okay. And did you save that? You know, maybe this could be that. So
I
did. Might be working too. I don't know that.
The other side of it.
Yeah.
It's great.
So I should save, right? Or is there anything else I need to do?
It should have. Yeah.
Okay.
Can you? Yeah.
Can I check on this computer? Maybe.
or just a poster.
This computer, yeah, it's not showing up on this one.
What's the website?
That's about enough to say the title. Yeah.
What's the website?
It's almost hard.
You mean?
Harvard.edu/, and then the little thingy, tilde, and geochem/webcast.hu.
I thought they were really not good.
I've like did it before, and it's fine. Like I know
Oh, it's showing up on here.
Oh,
How long are they?
okay.
So maybe
Rachel is
just into your cache or something. Do you want to put a link to it? Like,
Can you put the link underneath of it?
yeah.
I'm trying to think. Yeah, that would be good to put like the direct use. Like, yeah. Maybe just in parentheses next to Monday's session or something.
Yeah. Sorry.
I remember that. So I always make sure I'm like, the problem is doing a teaching that's really messed up.
Oh God.
It's great. I love it. I can actually. I've never struggled to hit anything like that. So I love Americans who talk like a lot of people really quietly. I'm constantly describing things like my head is like actually had through it. No problem in America.
You already put these on that computer?
Yes.
Okay, so we're gonna get one more.
Okay.
Yeah, okay, that's good.
So glad I
I'm putting this here for you. Thank you.
Yeah, not bad.
Oh my God, thank you.
Okay, at least one more talk and then the poster intro.
All right.
How you doing?
I have
Awesome.
a link on there, so it says click here for video.
So beautiful. Look at you.
Remembering my HTML.
Oh, I see. Where are you?
Wait, that's not the.
Oh,
Yeah.
got the wrong
So
one.
it's too fat. We have to actually unplug the microphone to get the.
Where's my name tag? Oh, there it is. Have we found Brenda? Laser pointer.
When did you come in?
Do you want me to just replace the folder with this new one then?
What?
Do you want me to replace the folder?
No. So,
Oh, okay.
you just
Oh, this one.
that one, and then the Malode is a top. Also.
Okay. So just put that
Yes.
in the Monday morning
Yeah.
folder. Okay.
And you got the posters.
Yep.
Some reason it's always
I might put the posters in here.
Rich leave the tape by any chance?
Do I what? I don't know.
No, I couldn't. Oh, that's fine.
Sorry, it's taking forever to eject. This is a very slow computer.
Yeah, all of it.
I just don't. Should I open up all the presentations at once so they don't have to load, or like?
Missing the chaos.
I don't know. It's working on my on this computer. So I put a link underneath it. Yeah, I saw the link. Okay.
Is that a setting though? We changed on the live stream.
Okay.
Yeah. Let's check that.
It's really good. I mean,
Well, I have it.
the red stars. So that means we have to do extra work and help people.
Like,
Okay.
More or less.
can we go check out the live stream settings?
Oh my God, I'm sorry.
Or maybe it's
Okay.
Here.
Okay.
the cap for this.
It's right there.
Oh, okay.
Melissa always has the answers. Yeah, then you check that box or does it not let
It doesn't let me.
Really? What does the question mark say? You have to go to like the account settings.
Okay, if everybody can take their seats.
Should we just start the?
We did so great. What?
Yeah. Well,
We can work on it the next break.
did Hannah set this down for me?
What?
Did Hannah set this down for me?
Oh, Makoto. Is that for you?
All right, if we can all get to our seats, we're
hungry.
gonna get started.
You want half?
I want to welcome you with great enthusiasm to this 9th International GeoScan meeting. My name is Daniel Jacob. I'm the GeoScan model scientist. I want to thank all of you for being here, particularly many of you have traveled from far away. I want to thank the agencies that have made this meeting possible: NASA, NSF, NOAA, EPRI, NCAS, and Harvard University. And most of all, I want to thank the ground team, consisting of my assistant, Brenda Mathieu, and all of my grad students who have been pitching in to try to organize this huge meeting. This is actually a much bigger meeting than we've had previously. We had to move our venue, and the logistics are quite a bit more complicated. Just remember, this is a grassroots meeting organized by the GeoScan community for the GeoScan community, and enjoy it as such. I'm actually really excited about this meeting because a lot of things have been going on in the GeoScan world. And just to illustrate this, I have this piece of eye candy that was produced by Matt Evans' group at the University of York, and that shows an animation of GeoScan running at 12-kilometer resolution within the GeoS5 system at NASA Goddard, and that was published by Liu Hu et al. In a paper last year. I don't think that anybody has ever done a full-year simulation of detailed tropospheric chemistry at that resolution. It actually looked pretty good when we compared it to observations. More on that later. We have an action-packed agenda. We have a lot of oral and poster sessions. We're very lucky for our oral sessions to have distinguished keynote speakers, Joel Thornton, Anne-Marie Carlton, and Steve Wofsy, who graced us by their presence. Also, those sessions will be to learn about new science and about new model developments. Because we had to change venue, the poster session is going to be right across the street in Maxwell Dworkin, where we usually have them. We have dedicated poster sessions in the evening of each day, the afternoon of Tuesday. But in the meantime, by all means, go hang out there and enjoy the posters. Beyond those sessions, we're going to have working group meetings that are very important to attend because they set the development priorities for GeoScan for the next few years. Those development priorities are set by you, so we look very much forward to your input on that. We'll have model clinics to expand the GeoScan skills, the support team help desk, and other things. But with all of this, I hope you'll take some time to be a tourist. You know, you're in Harvard, you're in Boston. These are nice places. Actually, if you just go 2 floors up by the back stairs, you'll find yourself in the Museum of Natural History of Harvard. Really nice, and I guarantee you a surprise when you step out the stairwell on the 3rd floor. Okay, let me begin by saying that GeoScan is much more than a model. It is a community. A community of users who try to further our knowledge of atmospheric chemistries and related issues for science and policy, and in the process, test the model, falsify the model, contribute new developments, and this is how the model progresses. Now, the way this is structured is that at our IGC meetings every 2 years, we set model development priorities, group of working groups. And this is a very important job for all of you, because you're going to provide in this manner a blueprint that's going to guide our development activities for the next 2 years. In between IGC meetings, we have a GeoScan steering committee that meets on the phone every 3 months that reviews the implementation of the priorities and works with the GeoScan support team
to make sure they're implemented properly. The GSChem support team obviously plays a critical role in all of this. They support the users with model code and maintenance of the data. They run benchmarks on new developments. They convert whatever the users give them in terms of new developments, in terms of some understandable code. And then they produce new model versions with extensive documentation that are then served to the user base. In all of this process, we emphasize user support and community spirit, nimble innovation. As soon as the development looks good, we try to put it in. We're going to stay state of the science always. Strong version control. There's no myriad different versions of GSChem floating around. This is very, very important, because otherwise you never recover. We actually don't even very much like to have options in GSChem. And very strong documentation and traceability of the model. At this point, I want to spend just a little bit of time to recognize the people on the GSChem steering committee and the support team that make everything happen. First of all, on the steering committee, we have the model scientists and the working group chairs, who give selflessly of their time. There's my co-model scientist, Randall Martin, model joint scientist, Devin Hensley. Everybody's here at this meeting, by the way, so you'll get to chat to all of these people. Nested model co-scientist, Yuxuan Wang Lin Zhang. WRF GSChem model scientist, Sun Mei Fu. Aerosols working group co-chairs. We used to have working group reports at the beginning of the meeting. We're not doing this. This is why I'm giving you the picture gallery here. So we have Becky Alexander, Colette Thiel, Jeff Pierce, Feng Chun Yu for the aerosols working group. Chemistry working group, Matt Evans, Darren Anderson, Lu Hu, Jin Shu Mao. Emissions and deposition working group, Emily Fisher, Jin Tai Lin, Eloise Murray, Dylan Millette. Chemistry Persistent Climate Working Group, Jeff Geddes, Handiao Li Murray, Anna Sty. Carbon Working Group, Kevin Bowman, Dylan Jones. The Joint and Data Simulation Working Group, Devin Hensley and Jun Wang. Transport Working Group, Hong Yu Lu, Andrea Malode. Mercury and POPs Working Group, Jenny Fisher, Chris Holmes, Yongshu Zhang. High Performance, GSChem, GCHP Working Group, Seti Stem and Randall Martin. And then we have a new stratospheric working group that's going to get organized this afternoon with Dylan Jones and Sue Strand as leaders. Finally, we have at-large members, Prasad Kasibatla, who's been with GSChem since day one and has contributed a lot to development, and Christoph Keller, who's our liaison at NASA Goddard, and also the famous developer of Hanko. So with this, and the GSChem support team, of course, makes everything happen. So we have Lizzie Lundgren, Melissa Sulprizio, and Bob Yantoska at Harvard, who do general model management, and Bob Yantoska is also in the steering committee as model engineer. We have Jun Meng at Dalhousie, who does the curation and management of the data. Liam Dindal, who's involved with the GSChem High Performance, GCHP, and Yanko Davila, who has been supporting the model joint for a very long time. These are the most important people in the whole GSChem operation. Okay, now all users are familiar with what we call GSChem Classic. GSChem Classic is a standard version of a model that's driven by meteorological data from the NASA GEOS system that's maintained at the Global Modeling and Simulation Office at GMAO at NASA Goddard. And we have either the MERA2 or the GeoSFP data that are supported. And with these data, we solve the chemical continuity equations on either the global domain or various nested domains at a native resolution or at coarser resolution. And solution of the chemical continuity equation involves a number of modules, including transport, emissions through HEMCO, chemistry, aerosol microphysics, if you so choose, and deposition. And we have also a model joint that includes all of these modules and allows you to do sensitivity analysis and various inverse model applications. The model has a lot of versatility. Apply it to tropospheric, stratospheric chemistry, carbon gases, mercury, POPs, and other things. I'm glad to report that over the past couple of years, we have implemented essentially all of the recommendations that were put forth at IGC9. The latest version that's currently undergoing benchmark is 12.4.0, and that includes grid-independent emissions. So that emissions that depend on environmental variables such as lightning, biogenic emissions, sea salt, soil dust, are the same at whatever resolution you run the model. Nice, you don't have to apply any scaling factors. It also has, this was led by Randall Martin's group at Dalhousie, Jintai Lin's group at BKU, Colette Hill, David Ridley at MIT, and Lee Murray at Rochester. We also have updated Aerocom volcanic emissions up to today, and this was provided by Christoph Keller at the NASA Goddard. And then we have the FlexGrid implementation, which was developed by Jiawei Zhuang and Melissa Soprizio, in which we read now the meteorological data through HEMCO. And that allows us to do a bunch of things. But the most exciting thing is that it allows custom nests that are defined at runtime. So you don't actually need to be stuck with the East Asian window, North American window, European window, or whatever. You can do whatever nest that you want. Nothing has to be pre-cut. Very, very, very nice, very powerful. In fact, we've had a lot of software engineering advances in GeoScan over the past couple of years that have really been mostly under the hood, to the point where many of you may not be familiar with them, and that's a testimony of the skill of a GeoScan support team. For a while now, GeoScan has been grid independent. That is, although you may think that it operates on the lat-long grid, actually, if you're using the GeoScan Classic, actually, it applies on 1D columns, which means that you can use really any grid resolution, any free grid resolution that you want. And that actually enables some very important things. One thing that it enables is distributed memory parallelization, so MPI. And this has allowed, in particular, the development of GCHP. And that has been led by Seb Eastham, by Mike Long, and by Lizzie Lundgren. And that allows GeoScan simulations to be done on hundreds of thousands of cores with excellent scalability. And so it allows you to go to very high resolution. It also allows having the model operate on 1D column, allows the model to be interfaced with any kind of meteorological data and to serve as chemical module in weather and climate models for online applications. And so we have maturing first interfaces for this with the GEOS system, that's the eye candy I showed you in my first slide, with the Beijing Climate Center, GCM. We have the WRF GeoScan in the data stage and CSM GeoScan under development. You will be hearing about all of this. We have gotten rid of dependencies on proprietary software. So now the model can be compiled with G4tran. All the output can be processed with Python. We have a collection of routine that we call GCPy that will process GeoScan output to generate the plots that you're familiar with. And one important thing that this has allowed us to do is to port GeoScan on the Amazon Web Services cloud. And this was done by Jiawei Zhuang, and it's perfectly mature. It's actually very well supported. You can run GeoScan Classic for pretty cheap on the Amazon cloud, right out of the box. Don't even need to compile it, just run it. Finally, we've done some things to protect ourselves. We now have an open license for GeoScan. That just means that no company can come in and say that GeoScan belongs to them and then charge us for using it. And all of the developers over the history of GeoScan are owners of GeoScan. So contribute a little piece of code and then you become an owner. You're listed on there. And then we document it with DOIs because that's what's often expected now in papers. In a few minutes, let me tell you a little bit about the coupling of GeoScan with weather and climate models as a chemical module. This is extremely important. Now, what I'm showing you here is kind of the standard GeoScan, where we take in meteorological data on any three-dimensional grid that we specify at runtime, although you may not be aware of it, but that's actually how it works. And then the model does its transport using the meteorological data, and then it does the local updates based on chemistry, emissions, and deposition. That's what we call the GeoScan module. Now, what we can do instead is to rely on a weather or climate model to do the chemical transport together with the dynamics, coupled with the dynamics. And of course, that has a number of advantages. It brings in a number of complications, but it has a number of advantages. The very important thing here is exactly the same chemical module is being used in both cases. Exactly the same code. Now, what that means is that all of the flow of innovation that comes from the GSChem community of atmospheric chemists using the offline model because it's simple to use, then flows effortlessly to the Earth system models and the weather models. And in that way, their chemical module never gets out of date and is always referenceable to the standard version of GSChem. There's a version number. Now, we just got awarded a new NSF project to couple GSChem with NCAR CESM. And this is going to be very important because now we will have the community-supported chemical model, GSChem, together with a community-supported Earth system model, CESM, that's designed for use by a broad category of scientists. And in the same way that we developed the same thing with WARF, and Chumeku will tell you about this later on, we now have an incredible array of capabilities for running GSChem at all kinds of resolution, coupling chemistry and climate, and so on, comparing different modules. Now, what does this mean for the future of GSChem? Well, the way I see it, we're always going to have one scientific base, which is going to be the GSChem chemical module. Single code for all implementations, state of the science, extremely benchmarked, traceable, highly documented, and then you can use it for various things. You can use it in the standard GSChem classic mode. Really easy to use, to install, simple to modify. You can use it on the cloud. The joint capability also available. You can use it in the high performance mode, which allows you to go to very high resolution, which allows you to access more accurate transport. And we're presently developing the joint and cloud capabilities for this. This is done particularly by Kevin Bowman, Davin Hensey, and Xiao Zhuang. And then we would have GSChem in weather climate models. And here, more and more, we have a number of these models in which GSChem provides a capability. And this has various advantages in terms of chemistry ecosystem coupling, access to any metrology. Resolution is very important. You can run WARF at 1 kilometer resolution, this GSChem chemistry. Really nice. And then, of course, for chemical data simulation and forecast, and this is what is used in particular at NASA Goddard. This is my final slide. And I just want to make a pitch that the continued success of GSChem very much hinges on its user. GSChem is a grassroots community model. You own the model, and I want you to feel that way. This is very important. You contribute to the model simply by using it. And it's wonderful if you falsify the model, if you report bugs, that's great. This leads to model improvements. You may develop a piece of code in the model. And if so, please contribute it to the standard model. I guarantee you a lot of citations and a lot of appreciation from the community and some co-authorships. Be generous with co-authorships and citation. That's the reverse side of the coin. Contribute to working groups. Contribute to model development in that way. I really much look forward to what we're going to achieve over the coming week in this regard. In case a GSChem meeting every 2 years is not enough for you, we now have regional GSChem meetings. We had a very successful meeting at Newest last May. It was organized by Hong Liao, and it was very successful. We're going to do it again next year at the Newest. I haven't checked with Hong, but I think she's on board. And then we're going to have a GSChem Europe meeting in June, and that's going to be organized by Matt Evans with Eloise Murray and Paul Palmer, and probably at the University of York. So with this, thank you again for being here, and
all right, so Danielle asked the Swiss guy to keep track of time for the first section, so I'm going to do my best. So we have the signs, and for the first session, I will do after 7 minutes. I give you the 2-minute mark, the speaker, and then 9 minutes stop, because usually there are not too many questions in the first session. So that's how we're going to do the first session. And so let's just roll on with Randall Martin as our next speaker, and he will talk about GCHP. Randall. And next.
Okay, well, thanks to a large community effort, most notably Seb Eastham and Lizzie Lundgren and Mike Long, the next generation version of GEOS Chem, known as GCHP, is ready for use. So to remind you, this project builds upon or is motivated by the immense growth that's going on with GEOS Chem, some of which we've heard about from Danielle already, we'll hear about throughout the week, with more sophisticated representation of chemistry, with additional tracers, with finer resolution, all of which require additional computational resources. And this is exacerbated by the fact that CPU speeds have stalled over the last 15 years, such that the traditional GEOS Chem Classic that parallelizes over only a single node has become too slow for many applications. GCHP is designed to address this issue. It builds upon the growth in the availability of cores and exploits a distributed memory framework to enable parallelization across large numbers of cores. At the same time, the meteorological representation has been upgraded from a traditional latitude-longitude grid to a cube sphere framework, upon which NASA GMAO conducts the GEOS assimilation, leading to a more accurate representation of transport and of the GEOS system. To give you a feel for the current performance of GCHP at present, I'm showing you here some work led by Seb Eastham, and you can see in dashed GEOS Chem Classic with limited parallelizability. But in solid, you see GCHP, which with additional cores offers faster runtimes. It's especially apparent at fine resolution. So if I could draw your attention to purple, the C180 simulation, roughly 50-kilometer resolution, and you can see excellent scalability. Now you're noticing, I'm sure, that at coarse resolution at present, that there's a modest scalability. And this can be understood by examining the processes that contribute to computational need. So on the left, you're seeing a coarse resolution simulation, roughly 25-kilometer resolution. And at that coarser resolution, neither chemistry nor advection are large drivers of computational need with large numbers of cores. Rather, input, which had not been initially parallelized, serves as a bottleneck. Don't worry, this is soon to be addressed thanks to development of a parallelized version of input led by GMAO, who've developed a parallelized version of the ESMF framework, or system modeling framework, known as MAPLE, that Lizzie Lundgren is currently implementing into GCHP. So this will soon be solved. But at present, already at fine resolution, look on the right at C180, roughly 50-kilometer resolution, you see excellent scalability for the processes that drive runtime, being chemistry in purple or advection in yellow. A 1-month simulation of GCHP at C180 resolution requires only a day of wall clock time at 500 cores. To test this further, Shaiwei Zhuang recently took GCHP up into the Amazon cloud and conducted a test simulation that initially neglects input, so neglecting that bottleneck that is yet to be fully solved. But doing a test on the other processes, and you see excellent performance up to 1,000 cores with a performance that's comparable to NASA's Blaze supercomputer. So this provides the prospect of the future large-scale accessibility of our community to GCHP through the cloud. Now, don't be concerned that these technical developments will change GEOS Chem in a way that you're not anticipating. Rather, GEOS Chem is GCHP. All of these technical developments have been occurring under the hood. The very same chemistry of GEOS Chem that you're already accustomed to is what is being accessed by GCHP, that very same code that we heard about from Danielle. Furthermore, GCHP is ready for use. To test this, Shunwei Xu recently downloaded the GCHP source code onto a Computes Canada server known as GRAM, conducts this full chemistry simulation that you see here on 860 cores at C360 resolution, so 25-kilometer resolution at the global scale. You see this unprecedented spatial structure that has been previously inaccessible to our community, that is now available. now you see yellow for mineral dust, blue for sea spray, green for organics, black for black carbon, and red for the sulfate nature of the system. Now, you've noticed that I've been switching across a variety of different resolutions during this talk already, and if the natural emissions were varying with resolution, the dependence on meteorology, think wind speed raised to a power, would lead to a variation in source strength that would confound or confuse comparison across different resolutions. But again, thanks to a large community effort, that the native resolution meteorological emissions for all of these different natural sources have been archived for both GEOS-FP and MIRA-2 and are being made available to all other resolutions, thus enabling a consistent representation of emissions across all of these different resolutions. So, in summary, I'd like to leave you with the exciting opportunity that exists for all of you to contribute to GCHP and enhance the scientific growth of GeosChem. There are a number of ongoing activities that we'll hear about throughout the week that are, you see it below, that focus on increasing accessibility and utility of GCHP. There's a dynamic clinic led by Seb Eastham and Lizzie Lundgren that will be featured later this week for those of you that have further questions. GCHP is offering you the computational framework, but its ongoing success will rely upon your scientific ingenuity and that wonderful collaborative spirit that pervades this community. Thank you for your attention.
We have time for a question or two. If you got a question, just speak up, and then maybe the speaker can repeat it as well. Questions?
Do you think we've compromised usability by the community for taking advantage of all of the new science that we've got?
Oh, rather, I think that we've increased utility by the community by having the option to access these additional resources. GeosChem Classic remains as is, and if the community prefers to access GeosChem Classic, there's no barrier to doing so. But rather, we have this additional option for increased resolution, increased sophistication in representing chemistry.
So I think this is amazing. I have a question in the context of these archived editions at native resolution. I understand the rationale for that, but when one thinks about coupling to CSN or my understanding from Daniel was we think of the GeosChem module as both the chemistry modules and the emissions. Is the idea still to use native resolution archived editions with, say, CSN, which might introduce a incompatibility with the meteorology?
So that's a good question, and I don't already know the answer to that, but rather I think that that's something that we should discuss as a community and identify the best path forward with understanding the trade-offs between having variable emissions upon different meteorological simulations. What do we want to define as GeosChem? Is it chemistry? Does it include emissions? And so I look forward to more discussion on that topic.
Right, great. So let's thank Daniel again. Our next speaker is Tung, and she will talk about your GeosChem.
Good morning, my name is Tung Fu. I'm currently at the Southern University of Science and Technology. And I'm really excited to tell you about this major development that we've been doing in my group, which is coupling WOLF to GeosChem. And before I begin, this is majorly made possible by two excellent students, Haipeng Ling and Xu Feng, who you will hear from at the model clinic this afternoon at 3:15. In addition, we received a lot of technical support from the GCST, so thank you. We were motivated to do this coupling primarily because as a person who's interested in regional air quality, previously we were only able to do GeosChem at high resolution over some areas some of the time. And it is possible to develop custom domains, but there's a lot of overhead associated with that. And in addition, it's not possible to do meteorology chemistry interactions. So by coupling to Wolf, we provide flexible grid systems. We can run at resolutions on the order of 100 kilometers down to a few hundred meters using Wolf LES capability. And by coupling to Wolf, we can now do hindcast and forecast driven by initial and boundary conditions from NSEP, EC, and CSM and other climate model outputs. Last I checked, EC goes back to January 1st, 1900, and obviously using CSM, you can do paleoclimate and future climate simulations. And using nudging, you can mimic the effect of the simulated meteorology at high resolution. And more importantly, because Wolf is already coupled to a lot of land and ecosystem modules, it's made relatively achievable to do atmosphere, chemistry, land ecosystem studies in the future. And what about current Wolf and WolfChem users? They mainly benefit by having just chem as a state of the science, well-documented, traceable GCST supported chemical module. And now we have just chem as an abstraction layer. It can provide consistency when coupled to both CSM and Wolf. And in particular, because Wolf is already adopted very widely by the large meteorology community, by coupling to GeoChem, it provides some easy access to air quality applications. So we started out with a very specific initial goal and a very specific development guideline. We want the coupling structure to be easy to use, massive and parallel, and ready for the future. So we started by realizing what the regional nested grid GeoChem can do currently with two-way coupling further down the road. And a really important part of that is we want to make the coupling structure as independent to both pair models as much as possible, so that either pair model can be updated independently. So this way, GeoChem can stay state of the science relatively easy. And we use GCHP technology to couple that to Wolf. However, in particular, we did not use any of the ESMF libraries. And running running Wolf GC is currently identical to the process of running WolfChem. It's fairly easy and it's free and open access. So this is the coupling structure. We start with the Wolf code. And here is the point of coupling to the chemical module. If you've run WolfChem previously, this is where Wolf is coupled to WolfChem. And then we take the GeoChem code off the shelf in this coupling structure. And the major development effort is in this development of the state conversion module and the state management module in distributed memory. And that talks to both parent models with no direct link between those either models. And a major accomplishment in this is that this coupling structure currently has Wolf and GeoChem code completely off the shelf. No further modifications necessary. So this is an example of the Chinese PM 2.5 simulation compared side by side with the GeoChem classic nested grid and the Wolf GC. These two simulations are done using the exact same chemical module. In this case, Wolf GC is nudged by surface meteorology data to mimic the simulated meteorology, and the resolutions are similar. So you see that these two models perform roughly the same. There's a slightly larger overestimate in the GeoChem classic. And one of the reasons for that is that using Wolf, we had a better representation of high resolution pollution meteorology. In this case, we look at the PBL height in the net data driving GeoChem and the net data simulated by Wolf. You see that the PBL height is much better represented by the Wolf GC. In terms of performance, this is a wall time comparison between Wolf GC and GeoChem Classic. You see that in the Wolf GC, GeoChem is run much faster than in the GeoChem Classic. And the reason for that is because we're using GCHP here, which has an MPI parallelization, which performs much better than the OpenMP. In addition, in GC Classic, transport is taking a lot of time. Surprisingly, using archive metadata is no longer saving us in time compared to running dynamic model ourselves. And in addition, the coupler is extremely lightweight. It adds almost nothing to the computation. Okay, so future plans and challenges. We've released an alpha version in January this year. And as you can see, WolfGC can already do what the GC Classic nested grid simulation can do. We are still working hard on the nested grid capability. This is where you nest several domains to achieve higher resolution. This turned out to be much harder than we thought. So we're still working on it, aiming for a beta release with that capability later this year. And we're also working on two-way coupling. That is the aerosol feedback based on bulk aerosol mass. We're thinking about building a more general binding in the coupler. And perhaps at this meeting, we can talk about more complex two-way coupling, such as the coupling to APM or Thomas. And finally, we welcome collaborations. This can either be research projects using WolfGC or joint effort in model development. We're starting to think about adaptive chemical mechanisms for higher resolution simulations in GISCAM. We are also hiring research scientists, postdocs, and software engineers. We currently don't have a support team, but we're building that. So that's it, and hopefully you will consider trying WolfGC for your next project. Thank you.
Are there any questions?
So the question is, what's causing the overestimation of PM 2.5? It could be a number of things. One is the meteorology. GC Classic in particular, the simulated data is underestimating the PBL height. The other thing is China, over the past few years, has gone through a lot of changes in emissions, and the inventory may not have fully captured that. So in a lot of cases now, we are actually overestimating PM 2.5 in China, not underestimating.
So this is really excellent. And you mentioned that, you showed the convection PBL depositions on the GSM side, and then you talked about limited physics options. Can you talk a little bit about what the limits are on the physics options and land surface models on the work side?
Okay, so Wolf offers a lot of physical options. In theory, you can use any of those. Because of the coupling structure, right now, in theory, you can just pick and choose whatever Wolf version you want, whatever physical option you want, and then just drop it into the coupling structure and it will work, in theory. There are some fine points to that, such as convection and maybe PBL mixing, but theoretically, any of the options available in Wolf you can use.
Great, thank you. Next, we have from Harvard. He talks about GISCAM.
So I will present a material and operational capability to immediately run GISCAM on the Amazon Web Services cloud. So our project is motivated by the fact that although GISCAM really aims to be user-friendly, but users still face all kinds of difficulties. For example, if you are new to GISCAM, and you first need to properly configure the model, which basically means fighting with mysterious errors. Then you just spend days and weeks just downloading this huge amount of input data to drive GISCAM, depending on where you are. And finally, some research groups just don't have very many resources to run big simulations. And even if you have been using GISCAM for a while, those changes don't go away. Because we update the model so frequently, and with every new model release, you will need to pull new input data and reconfigure and debug the new model code, and even sometimes relearn the model as if you are a new user. For example, it took very long for early users to transition from the early version 9 to version 10. Because we, basically Crystal, has added a new harmful emission code and totally reorganized the input data structure. Similar changes can happen with the new nested diagnostics and the custom nesting with FlexGrid and GCHP. But all those are important updates that will either simplify workflow or open new opportunities. So we really want to deliver those updates to users very easily. So my solution to these challenges is to use cloud computing to provide easy and immediate access to the latest standard JOSCAM that is complete into datasets. So on the cloud, you can request the so-called virtual machines with pre-configured JOSCAM that is ready for you to run. So no more software bugs. And you can also perform the computation just near the data repository already in the cloud and without suffering from the slow data transfer from hardware to your institution. And finally, those cloud vendors like AWS are providing virtually unlimited resources to run the model. So no more waiting in the queue. So as an important step in this project, Harvard has really signed an agreement with Amazon Web Services to host the complete more than 30 terabytes of JOSCAM data on their cloud that can be easily accessed by all the users. And we further provide a easy-to-follow tutorial. And a beginning user can finish a demo workflow, including running a short JOSCAM simulation and visualizing the model of the data in just half an hour. And this is according to a user testing we conducted at Harvard. So you will wonder how much does the cloud cost? So for small simulations, the costs are pretty low. So for a 1 year global 4x5 run, it costs you $30 US. And a global 2x2.5 run costs $120. And this can be largely covered by the free $100 per year student credit offered by Amazon. So if you're a student, just try it for free. But if you run very expensive simulations, then this can indeed cost a lot. In this case, I recommend checking out the AWS Research Credit Program. So Amazon actually has a lot of representatives from many universities, and they can help you work out a proposal. So if you already have your powerful local cluster, we don't want to replace it. You just treat the cloud as an additional utility that you can rely on sometimes. For example, the cloud is the quickest way to test the latest model and the complete input data without messing around your local environment. Then you can easily migrate the JOSCAM environment across the cloud platforms and your local server using a so-called software containers like Docker. And then the cloud also allows you to easily share your model simulation with other people if you give them the access. So the simulation can be easily reproduced by anyone. So you can also use the cloud to deal with temporary surges in computing demand. And finally, the cloud will be a very easy way to deliver the much more complicated GCHP. So Randall has already shown you that we got very promising results of running GCHP on Amazon Web Services. And so our current major limitation is the slow I/O, but we are working on that. So we expect to have a mature cloud GCHP capability in about a year. And I also want to point out that the cloud opens a lot of new opportunities beyond running the model itself. For example, agencies like NASA and NOAA are all start to share huge amounts of data through the cloud. And this might unlock some opportunities that might not be possible before due to compute and data constraints. So for more information, please see our upcoming paper on BANS and attend those cloud computing related sessions. Thank you very much.
What a time for questions. So with the, I'm from the GMO, so I'm particularly interested in the GEOS data. They're now in the cloud to run GeoScan. Are those data available to many other people as well if they want to know where they are? Because one issue we'd like to do is get them. If they're there, then this is solved.
So this question like can users download the data in the cloud to their own servers? So currently Amazon is hosting those data for free, but in order for users to pull this data out of the cloud, they will charge you some money for downloading that. But they also allow like active users to waive some part of that money. So the cost is about like about $50 per terabyte.
Maybe related to that question, one question that I have, the $120 that you showed, was that including downloading the
Right. So in that example, I assume the user is driving the daily concentration fields for all traces. That's 3 concentration fields, and that's only about less than 200 gigabytes, so it's not that big. But if you need to generate lots of data, then the storage cost will be significant.
Any more questions?
What would be the feasibility of doing it on a different cloud server besides Amazon?
So this can be enabled by the so-called software containers, which will go more into in the model clinics. So that allows you to kind of deploy JOSCAM on different platforms very easily. So if you have like say recipients from Microsoft or Google, you can deploy JOSCAM on their cloud.
So in terms of the I/O, what do you expect the scalability of the system once you've implemented the parallelization of the I/O in the cloud context?
So we are now testing still implementing a new parallel capability from the GML Metal software. Like I haven't actually used that like personally, but I think the software it uses some dedicated I/O module that is more advanced than what we currently have. So I think it will. So currently we're actually getting slower I/O when we are increasing number of cores. So in Kasi it's kind of a constant I/O with the different number of cores. So at least we will prevent this like the I/O gets slower with more cores problem.
Any more questions here?
Very interesting. So you sure you run the GeoScam on Amazon and on Microsoft. I just wondering if we needed to change the code, compile, debugging, and test. How expensive is that? Is that feasible to do in the Amazon, or we have to do in the local machine, change and go to there? So
either way can be possible. So if you want to debug your JOSCAM on local servers, you can do that, and you can easily migrate your environment back to a cloud using the containers. And you can also like do your development testing on Amazon Web Services, because in terms of testing, you won't use a lot of CPU hours, and that tends to be very cheap. So the major cost mostly comes from you keep the model running for like many weeks, and that costs you a lot.
Nope. One more.
So it's a question like, can you guarantee that your model is running on the same hardware through the entire simulation? Yeah, so if I understand, so you're asking like we'll use a kind of share the same hardware with possibly other people that might impact the performance. So this was a problem before. So in the very early like literature, people see that like you get like worse performance because other people are sharing your hardware. But now AWS is rolling out some like so-called bare metal instances, which basically gives you like 4 sets with higher server. And it should solve this problem.
All right, great. Let's thank you.
Good morning. So when we submitted the titles for our presentations, it said, oh, you can always change this later. And then it came to getting the talk ready, and I realized I haven't changed it later. So I'm going to try to work in the words reaction, replay, and reanalysis into this. And being not really a chemist, reaction is going to be the hardest one. The objective of this presentation is to highlight the role of the GeoScam chemistry mechanism, especially the fast version we've heard a bit about already this morning, in our GEOS Earth system model, and I'll talk a little about the directions we're heading and the progress that we've made so far. About 15 years ago, which is about the last time I actually ran a model on a computer, we started two projects kind of came up independently. On this side, closest to me, we started working on the GEOS chemistry climate model. And on the other side, there was a field mission coming along, Intex North America, and Danielle said to me, oh, you could actually run all of these traces online in the GEOS system. So we actually did. And these two pathways have kind of set precedents that there's actually being involved in the atmospheric composition on both weather timescales and on climate timescales. And really, those have there's been a lot of communication and the capabilities have fed back on each other very clearly. But right now, I feel we're in a position where this could all merge together around this new GeoSChem capability that we have. So this has kind of come full circle, and it's wrapping up quite nicely. I won't go into the details, but the one thing I do want to say, a key person in both of these efforts was Eric Nielsen. Eric retired about a year and a half ago, so he's no longer with us in the GMAO. But really, a lot of where we are today, I have to say, is based on the work that Eric did in terms of the technology inside the models and getting us there. Helps to use this one. No, it doesn't. Okay. I somehow lost the slides on the screen. So basically, I'm going to start by showing some curves that's going to have time on the horizontal axis and the amount of ozone, total ozone in the atmosphere on the y-axis. And essentially, towards having a new contender for the chemistry climate modeling work on it, I'm just basically going to say that the the bar is pretty high on what we're able to do already. From the first, there we go, almost. Thank you. And I do this?
Yeah.
That one? Works. Great. So the first version of the chemistry climate model in 2006, we had ozone depleting as we went from 1990 to the early 2000s, but it was offset from observations by rather large amounts, and that actually decreased. That amount decreased as we went into a sort of CFC chemistry-dominated regime. As time has gone by, we've improved the processes. This was the change to GeoS9. This was, I think, getting some. It's all listed here, getting the very short-lived bromine compounds, volcanic aerosols, and also the QPO came in. That changed. And where we are right now, we've included more tropospheric chemistry. This is the GMI tropospheric stratospheric combo mechanism, the solar cycle and things. This plot was made by Luke Oman and Jin Liang at Goddard. So really, over the decade or so, we've really improved the simulations of total ozone. So as we go to a GeoSChem, and I'm hoping very soon we'll have one of these with GeoSChem chemistry, the bar's pretty high. I don't know where we're going to end up. So this is a good challenge for us. But already in the implementation of the GeoSChem chemistry in this model, we've actually led some improvements in the mechanisms, and they've fed back onto the code in the central repository that we're all using. This way. There we go. And then, of course, the other side of things, and the movie's not playing, so. Okay, well, this was supposed to be a movie. The new product that we now are putting out is this 25-kilometer resolution global composition forecasting system, which is based on the geometeorological analyses using replay. I got that in. So essentially, we're reproducing the analyses over time without actually having an analysis, having to do the analysis. So we're getting that. And 4 analyses per day, along with a 5-day forecast each day. And we're able to see that there's a fair range of skill in many of the surface meteorological fields that we're out. And this was going to show how nicely we get things like the diurnal cycles, the weekday-weekend changes, and things like that. I already said it's running at a resolution of about 25 kilometers globally every day and producing a 5-day forecast. And this is really this is a new product for us, and it's really illustrating the way in which code that's developed by the community is able to feed into our model and then get used in a product that's not operational in NASA, but it's a production system. Data are going out to NASA science teams and to the whole world from our products. See this one. This one's not working either. That's a shame, because this is the example essentially of the surface ozone analysis produced using replay. Yeah, using replay. You can, if this were running again, we've seen similar things already this morning, so it's not too critical. You can see just the fine scales that we're able to resolve, the way the transport catches the features, the emission features, and moves them around. You can see the diurnal cycle moving around. Just imagine.
You just send a few more.
It's all there. And that then comes to my summary. GeoScan really provides, or this new version of GeoScan really provides the pathway towards a sustainable modeling of atmospheric composition in our systems. We're exploiting this with GeoCF already. This is the first new product, that's been very different from anything else that we've put out in several years. The central repository that we have allows for easy code sharing with the research community, and I think this is a new paradigm for us in terms of we are now able to take code that's been worked on by a large number of people, getting the best of the developments, and we're able to use that, and I think there's satisfaction for people in seeing that code go through that way. But there's also value because as we use code in this way, in a really production system, we start to test it on a day-to-day basis, and then there's feedback to the code developers to be able to improve it further. And this is a really healthy two-way street that we are working towards here. And this is a pathway from research to production systems. I'm really hoping we're going to be able to use this GeoCF system, as we're running right now, as the basis for a 20-year reanalysis, I'll put that word in, of atmospheric composition, using a lot more assimilation of atmospheric observations from EOS and more. And I'm really, we're putting the GeoScan mechanism as a contender for the future versions of the chemistry climate model. And this, with the history of the work done at Goddard with the ozone hole and everything, this puts stringent demands on the stratospheric chemistry components of that. And then I managed to get the word reactions in. The reaction could be, are there any questions? It could be throwing run throughs, it could be anything. But I just want to add who else is here from the GMAO. Andrea, Christoph, Pamela, Emma, and Susan, who's actually not from the GMAO, but she's from Goddard and works closely with us. And you will see most of them at some point in the so I'll stop here and take questions.
Well, I guess we really have to up our mission game.
Yeah.
Are there any questions?
What's the timeline for the community getting access to the forecasts from CF?
So the forecasts, you mean like when they'll be able to get them totally, or how quickly?
Or just being able to download them and then being able to sort of use them?
Right. So the forecasts are actually on an open app server, the surface fields of these, and you can see movies of them pretty much as soon as they're ready. And you can also access the data. It's kind of there, but we haven't put out a kind of an official release yet, and that's partly because there is always one more thing to make it a little bit better, and partly because we've got busy with other stuff and it gets delayed.
It would be super cool for us to be able to sort of do a forecast with GeoScan for your, and just see what it looks like. So
absolutely, yeah, and I think, that's possible.
And just to be clear, this is with the gas phase.
All right. So right now we're in the situation where we're running the GeoScan with gas phase and aerosols, and we're also running the GoCard aerosols, which is our standard aerosol package. Now we can't. For us, it would be a major challenge to move away from using GoCard because that's what's coupling into the physical components of the model. So our longer-term goal is really to have an interface between the GoCard aerosol modules and the gaseous components of GeoScan. And I think that's really the solution that's going to work for us. And also, if we go to a more complex aerosol code in the future for getting two-moment cloud microphysics, right, that's going to be a pathway for us. This is a little more self-sufficient.
David, do you think the GMI chemistry and the GeoScan chemistry will coexist in the future in the GeoSystem?
We don't have any plans to retire the GMI chemistry. I think the question really becomes is, to me, moving forward, you have to make changes, and we've made a lot of changes. Now, to me, the question is really, when does the GMI chemistry mechanism stop being developed? Because we've got a tremendous development effort going on with the GeoScan mechanism, and to me, that is pointing to that being the version that we'll be looking at 5 years from now, unless something changes in the landscape.
All right, we will move on. Thanks to you. Our next speaker, Andrea Moran, also from the.
Hi. So I'm just here to give you some updates on what's going on with our different systems that have the drivers for meteorology. So GMAO staff, because if I put everybody's name who contributed to what's going on there, it would be 2 pages. So first is, this is at the bottom, here's the website where I'm getting this information from, but this is a useful website for everybody to kind of have. This is our near real-time systems. And again, as written at the top, these are the systems that are undergoing continuous upgrades, but this is the highest resolution of the systems that we run. And it gives a timeline for what system was running for which time period. The other systems, of course, are the reanalysis. MERIT-2 is the main one. MERIT-2 is running about 2 weeks, maybe a little bit more behind real time. And so just again, the website's more for people's reference than anything else. Since IGC9, we've done 3 different upgrades and 3 different versions of FP have been released. Again, sort of a little bit of a summary slide. All of this information is available through those websites that I showed on the previous slides. But as you can see on the right, the impact on the results in general, the forecast skill has been, increasing with each release. Just a reminder here, the note at the bottom is that the file spec, so what the files look like and things so far hasn't changed, even though we've increased from 25 to 12 kilometer resolution. We still have the 12 kilometer resolution available. I'm not sure what the timetable is for that changing, but in the meantime, it hasn't changed. Okay, and now, this is, I think, mainly what I'm here to talk to you about is this is what's coming. This is what's coming down the pipe in terms of FP systems that are currently under evaluation. Of course, analysis system data and ensemble upgrades and model upgrades that are coming. I wanted to highlight that second one here because I think that second one provides a solution to a headache that GeoSchem users have been having running at coarser resolution, which is with the implementation of the Grell-Freitas convection parameterization, this scaling down of the convective mass flux with resolution is substantially, it doesn't scale down. I have numbers here with the preset. So here we have, this is the horizontal resolutions, the equivalent grid size. Here's what the GF, the new scheme that's being tested now for new FP systems, does in terms of the convective and parameterized versus the total preset. And you can see here that this stays at this level in the 60s and doesn't drop off until we get down to quite high resolutions. And this is where we are now with the RAS. By the time we got down to C180, which is MERIT-2, we've already done this scaling down of the mass flux and the preset. And by the time we get to 25 kilometers, which is what the FP is running, we've squelched a lot of it. GF, it's still a robust system. So this taking the high resolution FP output and interpolating it down to coarse resolution and trying to use that to drive meteorology, that headache, I think, is going to be substantially diminished when we start to get this new system and these new systems. But in some ways, this new physics is going to be a little bit of a different animal than what people are used to. So here's a little bit of a heads up. The top plot here is the cumulative mass flux for the new system. The middle one is what we're living with now, and the bottom is the difference. So we're talking about, for instance, because of the implementation of the shallow convection parameterization, a substantial increase in convective mass flux. Here on the right is the turbulent transport, and that's been essentially decreased in many areas. So this exchange between the mass flux and the turbulent transport is changing a little bit. Just to get a sense for you guys of what this means in terms of transport, this is the difference in the radon simulation. And so what we're seeing with the new minus the old. So what we're seeing is a lot more transport from the surface up to the lower troposphere but a lot less transport to the upper troposphere. I'm not going to engage now in whether this is a good thing or a bad thing, but at the higher resolution. But just a heads up that the character of the transport and the split between the convection and diffusion is going to be quite different when this gets released. Just a quick set of results about this. Basically, these systems, a lot of these systems are being driven with to get increases in the forecast skill score. And if you look on the left over there, you see 850 millimar temperature anomaly correlation and RMS error substantially better. But on the right, you see that the bias is worse. And so this is an interesting issue that's being dealt with, and this is one of the reasons why the system isn't quite ready yet. One other thing that I just wanted to talk to you guys about, that this is still in the planning stages, is we're looking to work out some kind of a formalism to get evaluation of the constituent transport folded into the development process. We're looking to get tropospheric transport, interhemispheric, as well as the SF6 is basically targeted for our CO2 community. And so the idea is we want to test it in atmosphere only, in data simulation experiments, evaluate them all, and come up with a list of relevant metrics. This is a collaborative effort that's being led by Emma Nolan from the GMAO, including people from Chemistry and Dynamics Lab and Clara Orby from this. So this is still under development. We're going to discuss this more probably in the Transport Working Group meeting. So this is basically what I wanted to show you here. Here's my version of the who else is here.
Questions?
So, Joe, when we go to the Grail Freitas conductive scheme, will we have less of a problem of underestimating conduction in the offline simulation?
Yeah, and of course the resolutions.
Except that we have much less deep conduction we're showing.
Yeah, so that's where the thing is now. And so I think that this, they hadn't seen this radar picture until I made it and showed it to them. And I think that that may prompt some adjustments or things for them to do.
Yeah, I'm interested in some of the resolutions that you were moving for in the future. I know with you've also been working on the offline CTA. So what resolution does the IO structure essentially raise the capacity of the system to actually run? Where in other words, running online actually is the only way to move forward.
You know what, I don't know the answer to that, but I think we're there at some of the very finest resolutions that we're talking about here, despite using the parallel I/O that they're talking about having GCHP start to use. That's not helping get around that, but yeah. So I don't know exactly where, Kevin, but I would guess that we're there.
All right, great. Thank you very much.
Hi, everyone. So wow, we are talking about some very exciting developments in our model. One of which is the logo. But I must say, I think that, eventually there's going to be no reason for anyone in the atmospheric chemistry community not to use geochem, because all these things that are happening are, solving some major challenges. So it's very exciting. You've all probably seen this kind of cropping up in various places, including, I guess, wine bottles last night at the scientist social. Really good thing we came up with a square logo, I feel like, because otherwise it wouldn't fit on a wine bottle. But anyway, so after the last meeting, I believe, you might recall that we had invited the community to submit potential designs for a new logo. And in addition to taking that input, we also opened it up to a professional design competition and identified one particular designer that I worked with back and forth on in consultation with some feedback from the steering committee, and this is what we've come up with. So we have both the sort of long logo and a square logo, and we also have one for dark backgrounds, people who like dark slides. So we're really hoping to see these out in the wild now, and hopefully everyone can kind of get behind this one new sort of logo for the model and kind of avoid having lots of different versions of icons and things representing our model. So you can definitely easily grab this logo off of the main GeoScam website. And if you want any particular, the dark background one or whatever, you can't find something, certainly email me or the support team and we'll make sure that everyone has access to these new logos. So thanks very much. I'll take any questions.
All right, last but not least, we have poster introductions. So everyone who has a poster in that first session, please comes up here, and then I think we have we'll line through the back door. Okay.
Yeah.
Okay. Yeah.
I got
Exit downstairs on that side, guys.
They know what order they're in.
Hi everyone, I'm Lucian from Harvard. We have developed an adaptive chemistry mechanism that can reduce the CQ time used by the chemical solver by 40%. And you can see the relative errors after 1 year simulation of these species are quite small. And if you are interested, please stop by.
Hi everyone. So compiling GC9 can be a little bit tricky, especially for new users. And so I've been working on a new system for compiling GeoScam that uses a tool called CMake to automatically generate the scripts that compile GeoScam. And for a big project like GCHP, which has a lot of code that needs to be compiled, this makes it a lot easier to manage for developers, which in turn ultimately makes it easier for users to compile.
All right, so I brought a poster about the work that Matt Evans and I did, where we looked at can we use machine learning to essentially replace, and I'm sorry I did not use the GeoScam logo, to essentially replace the GeoScam chemical numerics in the model. We see this sort of like as a speedboat application for certain applications where we don't care exactly about the full numerical position. If you wonder if it works, stop by the poster, just talk to Matt or me. Spoiler alert, it kind of does, depending on how you use it. So I was slightly put out when Daniel stole my thunder by showing this figure in the intro. But there's a joint MIT Harvard NCAR project now to get GeoScam as a functioning online country module within CESM. This is aligned with and part of the CESM development goals for CESM 2.0. This shows the eventual end stage where GeoScam's components will be fully integrated with CSM, including using Chemco to drive all emissions and data input. This is a very early stage in the project, so I'm really looking for community feedback, ideas, worries, concerns, etc. Come along and see the poster if you're interested. I want to hear more.
Hi, my name is Taiwan P, and I'm from University of Toronto. So we work on fixing the convective transfer issues in GeoScam offline model. So we perform a sensitivity analysis and optimize the RAS parameter relationship. And we evaluate the performance of the optimized system using observations of radar. That's the GMA. Thanks.
Hi, my name is Roshan Park from Seoul National University. And showing this comparison, we found that GeoScam reproduce the observed hourly PM2.5 concentration quite successfully. But occasionally, it simulated too much PM2.5, especially during the nighttime. So in my poster, I'll address this issue mainly by focusing on meteorological feedback to the presence of aerosol, which might abate this bias a bit. Thank you.
have a coffee break and reconvene at 10:40. Thank you.
Good job, team. That was very first sessions that have gone far, far worse. Great work.
Yeah.
No, you're gonna turn on the video.
Because that'll show your face.
If it's on screen share, it shouldn't, but
Yeah.
so when you want to start, you just do the screen share. And it'll start sharing your.
Yeah, this button, and then open whenever you need.
talk I've been looking for most of this whole time. Okay. How are you, Elise? Are you Jerry?
Yeah.
Oh, good luck.
It's a rowdy bunch. We'll have to watch. I turned the mic back up so she could announce. So see if I have to turn it back down again or not. Like room mic.
Sounds really bad.
I know, but the people, well, when they're this loud, they couldn't hear.
Yeah. Did you turn it down or not?
I will when I'm gonna make sure Eloise isn't gonna announce anything again. Just make sure when they're ready to start taking questions, that's when you go and switch to them.
The PC doesn't update during the keynote. What could possibly go wrong?
I feel like all the people who are watching the webcast would be like, I've been there, though, you know?
Yeah. I'm going to try and speak over the din that's happening in the background. It's my great pleasure to introduce our first keynote speaker for IGC9, Joel Thornton. He's going to talk to us today about biogenic VOC chemistry influencing secondary organic aerosols. Thank you, Joel.
Okay, well, thanks very much to the organizing committee for giving me this opportunity. It's really exciting to be here. I regret not being here more often on seeing what's going on. So I didn't even realize on my Steve Fossum that you could change your title. So I went ahead and changed on my screen a little bit more general. Beyond biogenic VOC, but I certainly will talk about those issues. And I'm going to give you an introduction to something where GeoSchem seems to be doing really well at SOA. And then I will end with the perhaps more negative side of things. So yeah, we'll do a little sandwich. I'll give you some opportunity for positive, negative, positive, as we're told to do with our children and so on. So why do we want to think about secondary organic aerosol? This is just a snapshot of Eastern U.S. PM 2.5 composition. Organic aerosol is and even has been, it's becoming the dominant single component of surface PM 2.5. So from a policy standpoint, we really do want to understand what controls the abundance of organic aerosol, both in the summertime and also in the wintertime. Because as NOx and sulfur controls continue, if it's not the dominant component now, it may very well become the dominant component in the future. And so I'm going to talk a little bit about, first, actually, wintertime organic aerosol and what we think controls that component. And in part, we want to do this because in wintertime, it's colder, especially in northeastern United States. So in large extent, biogenic VOC emissions are diminished greatly or even non-existent. And so this then allows us to isolate the role of anthropogenic volatile organic compounds as a source of organic aerosol. You might think that wintertime is also a particularly dormant period, so conversion of volatile organic compounds into condensable vapors through oxidation may not be happening to the same extent that it would happen in the summertime. This is one of the questions that we had in the winter campaign, wintertime transport emissions and reactivity, which was an NSF-funded campaign that I was PI of and worked together closely with Liat Shea-Gray at University of Washington and other collaborators to fly the NSF C-130 around the eastern United States in the winter for several reasons, but one of them was to understand what controls aerosol evolution in the wintertime. And so Viral Shah, who was a graduate student at the time at the University of Washington, who's now here at Harvard working with GeoSchem, was using GeoSchem to help us think about what controls organic aerosol in the wintertime. And what you're seeing here is wintertime observations from the C-130 of organic aerosol abundance and the GeoSchem predictions that Viral came up with, both in the spatial scale and then the sort of agreement in the vertical. And actually, it's quite good. And you might wonder, well, what was he doing to make this work out so well? Nothing very complicated, and as a chemist, somewhat disappointingly simple, as we call it. What he did was actually use something that was developed by Alma Hodzik and Jose Jimenez, where anthropogenic volatile organic compounds, a surrogate compound, is co-emitted with carbon monoxide. Just here's the scaling, and then it's allowed to react with the hydroxyl radical, and it makes secondary organic aerosol at 100% yield. There's, of course, primary organic aerosol emissions in the model, but what you'll notice, actually, is that the enhancement in organic aerosol as air masses age away from emission sources actually looks strikingly similar to what was observed in summertime conditions, even in different regions, not just in the northeastern United States. So that's this blue wedge here. In the wintertime observations we made showed a continued enhancement of organic aerosol going downwind of urban areas, mostly where in the end, the organic aerosol is essentially dominated by secondary organic aerosol, even in the wintertime, not just in the summertime. And the agreement between what Baral's simple model of SOA formation in the geochem produced was strikingly similar to the observations in terms of the component of that organic aerosol that is secondary in nature. So that such a simple scheme can explain essentially the evolution of organic aerosol in the partitioning or breakdown between primary organic aerosol and secondary processes, is rather remarkable, somewhat surprising, one would think, and as I mentioned, somewhat disturbing. For a number of reasons, we would like to ask questions about how do emissions of other pollutants like NOx or sulfur dioxide, or what exactly are the emissions of the anthropogenic VOCs? What are the VOCs that are actually driving the secondary aerosol? So we can think about what future changes in those emissions will do to this particular picture. You might also think that it's surprising that secondary aerosol formation is as rapid as it is in the wintertime because we are limited by the availability of oxidants in the wintertime. And actually, the next talk will actually inform us about what we are learning about wintertime oxidation chemistry. The secondary organic aerosol is a phenomenon that is happening both in the summertime, also in the wintertime. And a simplified scheme seems to do a quite appropriate job for the now, but it's the sensitivity of these processes to other perturbations by anthropogenic activities that we are really most interested in from a policy standpoint, so we can understand to what extent can we control this organic aerosol, what way, how should we do it, and how will it respond to other changes, both in perhaps environment, climate, temperature, but also anthropogenic perturbations. Yes, so ultimately what we want to do then is connect the SOA that we observe forming in the wintertime or at any time of the year to specific precursors that we understand the emissions of, the chemistry that connects them to a range of condensable vapors where the oxidative processing in the gas phase produces a wide distribution of products, and this is where the complexity starts to come in. And as a chemist that we really like, but as what Baral showed us, maybe we can forget about. This seems confusing. We know we made tens of thousands of different compounds in atmospheric oxidative processes that have a wide range of saturation vapor concentrations because they have a wide range of functionality. And that functionality is going to determine partitioning into the condensed phase and the reactivity of the condensed phase. This may or may not be reversible, and therefore we may have continued processing of vapors that are partitioning partway between the aerosols. So the evolution should be complicated through the entire life cycle of the organic aerosol. We have condensed phase chemistry that I haven't even mentioned, and then potentially the role of planets. So in a model, we would like to write down that the secondary organic aerosol formation by a particular oxidation pathway and precursor is going to be represented by some yield of vapors that condense into the aerosol or react in the aerosol. There's going to be some lifetime due to losses. Those can be physical losses like wet deposition, dry deposition, and also perhaps chemical losses. like I was mentioning here, through the oxidation of vapors that are in equilibrium with the organic aerosol phase, and then transport. So there's a lot to get right. If we're trying to simulate secondary organic aerosol, and there's a lot of complexity. And what to do about that has been the challenge for our particular part of the field of atmospheric chemistry is how do we represent what we know is complicated in a way that accurately reflects and simulates what will happen to secondary aerosol in response to all sorts of possible perturbations, both to the gas-phase chemistry and also to the condensed phase chemistry. Okay, and in order to test our ability to make these simulations, we would want to then test what a model predicts for the sources of secondary aerosol in this way. And again, models basically doing that process that I just showed you before in different levels of complexity. So an influential paper for my group was this by Patrick Kim and his group, published back in 2015 as essentially an outcome of several field campaigns that took place in the summer of 2013 in the southeastern United States, with simulating, in this particular, this bottom panel, organic aerosol abundance and distribution. And what you'll notice is that in this particular version of GeoSchem, they attributed the sources of that organic aerosol. So we have, you'll see a very prominent role for biogenic VOCs in the summertime, and this is in contrast to what I just showed you for wintertime, which we think is largely dominated by anthropogenic VOCs. There are anthropogenic components, but by and large, biogenic SOA. This has been something we've sort of known in the field for many years, is that in the summertime, especially in the southeastern United States, we have a rich emissions of isoprene in particular, and also monoterpenes, that can get converted into condensable material like aerosol. So we have a very large role for isoprene in particular in this simulation, and a large role for isoprene reacting under highly polluted conditions in the presence of high nitrogen oxide concentrations. So my group, actually for quite some time now, has been essentially trying to come at this from an observational perspective and to produce that kind of pie chart, but using observations of the chemical composition of the organic aerosol, so that we can better test what the models are predicting for the sources of secondary organic aerosol. So I'm not going to spend any time on this slide except to say that we do a highly resolved chemical source apportionment of what's in the aerosol using online observations of aerosol composition and volatility. If you want to know more about that, you can talk to me. We have field deployed this in the southeastern United States, as well as Finnish boreal forest, urban areas, and more is coming. What this does is provide hundreds of unique molecular components in a quantified way, essentially hourly throughout at any location where we're measuring, so we can start to resolve local and also regional contributions to the secondary organic aerosol. What we require to do that, though, is a set of basically an understanding of where do each of those chemical formulas that we derive from our observations come from. So we do a range of chamber experiments. We're more than 18 now types of experiments that we've run using our same instrument that we use in the field, but then we basically do test scenarios in these chambers. We oxidize monoterpenes, specific monoterpenes or mixes of monoterpenes, isoprenes, sesquiterpenes, aromatics, and we use different oxidants, hydroxyl radical, ozone, nitric radical. We add NOx, we don't add NOx, we have aqueous aerosol, we don't have aqueous aerosol, we have acidic aerosol, we have non-acidic aerosol, and so on. Okay? And each one of these experiments is producing for us a rich set of molecular markers that allow us to then use as basis spectra in essentially a linear regression, where we then extract the contribution of that particular set of conditions, its contribution to what we observe in the field spectrum. So we are going to basically do a linear combination of each of these types of spectra that give us a connection then directly to its importance in constraining secondary organic aerosol at a particular location, or organic aerosol in general. So I want to
mention though that when we do this with specifically what I'll show you next, is that we're explaining about 80% of the detected organic aerosol mass. So there's about 20% we're not explaining. I think that's going to be important. We explain about 90% of the variability. So R squared, when we try to explain what's going on with 180 different unique molecular compositions, we explain 90% of that variability, and those compositions are explaining about 80% of the observed organic aerosol mass from an independent instrument, the aerosol mass control. Okay, so what do we see when we go to the Southeast United States? Granted, we've only been in one spot, so this is the problem with some of our observations. We can't compare it to an average over the entire region of the Southeast United States, but we're here during the SOAS campaign, led by Emery Carlton. Thank you very much for doing that. And what do we see? Well, part of this has been published before. The first is that by a large margin, we do see biogenic VOCs dominating secondary organic aerosol in general in the Southeast United States. But what is different here is that monoterpenes, according to our observations, are the vast majority of the source of that organic aerosol in this particular location. Isoprene is not unimportant, but it's a much smaller component than we had expected. This is something we contributed to Hauptmann Zheng's paper last year. What we're doing now is trying to give guidance to models of what chemical pathways are important for generating the organic aerosol from these different precursors. So it's not enough that we have monoterpenes as the dominant source of organic aerosol. How is it chemically that those monoterpenes are getting converted into organic aerosol? And what you find is it's been quite a puzzle for a number of different reasons. First is that we have a very large component without any nitrogen oxide contribution. That's at least is not necessary to explain what we observed. There is some, we do see organic nitrates that we have to replicate in our particular matter, but by and large, we can explain this with, you might call it canonical low-NOx monoterpene chemistry. There is clearly a role for dark chemistry, but we're dominated by photochemistry. And not just photochemistry, starting with hydroxyl radical or ozone. We have to have both of these operating simultaneously and actually in the right ratios in order to generate spectra that look at all similar to what we have in the field. So that has some significant implications both for how we were supposed to be learning about secondary organic aerosol in our experiments, but then also how we would go forward and put this into. In particular, we need to actually run the chamber such that the effective age of the aerosols photochemically is equivalent to 3.5 days of aging in this field. This is an outcome that we get from doing these kinds of experiments and comparing to observations in the field. Then we can then start actually testing timescales over which this aerosol has been residing in the atmosphere. I think that's going to be powerful for comparing to models in an online way. Okay, so just to remind you what that looks like, if you scale back and say it's all biogenic, things look really good. If you then say, well, what happens to isoprene emissions in the future and therefore SOA? Well, then things are not going to look so good. Or what happens to NOx emissions in the future? They've been declining over the past decade. Shouldn't this piece be declining substantially? It doesn't seem that we have then the right couplings to those other forcings of organic aerosol being described in the moment. Okay, so in our source apportionment, we can also do this on an hourly basis. We can create wing roses, and we can create diagonal cycles. And what you'll notice is that there's a strong component that is essentially invariant with time of day. This is what we would call a regional background contribution. This is the dominant component of the organic aerosol that we measure, and it's essentially monoterpene photooxidation in the presence of sunlight, OH, ozone, and a little bit of NOx. But not in a way that's NOx dominated. There has to be light, there has to be both OH and ozone going on simultaneously. We see evidence for fresh and local SOA formation by the fact of these strong diagonal cycles in certain cases, which tells us that it allows us to separate what is regionally important and what is locally important, but also that there is a dynamic aspect to SOA. That there are SOAs being formed and it is disappearing. And it's disappearing on timescales which are not consistent with just the weather event causing rain out precipitation. this is going to be a huge challenge for, I think, modeling to actually capture correctly. I'm not going to give the answer for how to do that necessarily. But I think it's an issue that has been invoked already by other experiments. It's out there, and what we're doing here is putting robust observational support that this is actually an issue that we're going to have to grapple with. Okay, so we're going to summarize, and if I have a few minutes, I'll either take questions or I'll go on to my third part. So we have basically a contrast of issues here. We have, in the wintertime, a simple, nearly chemistry-free SOA scheme captures organic aerosol evolution, both in terms of the ratio of primary and secondary. And this is actually, I think, the message of work going on in the group, which is that the simplified schemes don't necessarily work any more worse than the more complex. In fact, the more complex is time-consuming and is not actually producing necessarily better results across the globe. Here we've isolated out the biogenic component, and I think this is a really unique opportunity going forward, both for experimentalists, but also for models, because you get rid of that biogenic component. It's a little bit of a simpler system to allow us, somebody should go out and figure out what are the VOCs, and let's get this right. It seems to be a simple behaving system. But when we want to do policy relevant questions, this becomes an issue. And that's where we get to this. If we add more chemistry, are we adding the right chemistry, and how do we actually test that? Well, we're going to have to make more observations like this, I think, going forward. And this pie chart raises more questions than it answers, because in our experiments, we didn't do any cloud chemistry, we didn't do cloud processing. We're able to explain 80% of the mass of organic aerosol. So essentially, is what we're missing not important? That's an implication here. High NOx isoprene is dominant in terms of carbon emissions in the southeastern United States. It does not really appear to a significant extent, especially the high NOx pathways that we've tried in laboratory. The evolution on an hourly basis supports the use of dynamic SOA treatments, similar to a 2D BBS type scheme, of both gas and particle phase components, because we cannot get the SOA composition or the volatility correct unless we are aging it in our chamber. So this also informs the way we have to look at chamber experiments as their, in terms of their utility for going into models, is to what extent are we getting both the composition and the volatility right over the right timescales in both physical and chemical aging in our chambers. So some possible progress can be made by making more observations like this to allow multiple sites for a model to actually lock onto and test then emissions versus chemistry and so on. But also, I want to put a plug in for some things that we do know about monoterpenes being actually very efficient at creating secondary organic aerosol. And this is the world of autooxidation, which is a new chemistry scheme that I don't quite have time to talk about in detail here. But it's going to be a way that we can get prompt formation of secondary organic aerosol from monoterpenes. And if we add a little bit of aging to the model, this might be the strategy by which we can have, in the southeastern United States, where there is NOx and a lot of isoprene, monoterpenes under a low NOx situation, dominating the source of organic aerosol. Am I out of time?
You're out of time.
Okay. Good. Well, anyway, thank you for your time.
You are out of time, but we will allow 2 quick questions. I see Dylan's hand went up pretty quickly.
So, Joe, can you comment about these 18 basis sets from the mass spectra that you think to separate out these different source contributions? Can you talk about how much orthogonal you think those are in terms of resolving those?
Yes. So the question is about the orthogonality of the different basis spectra that we use from the different experiments. Not all of them are orthogonal. So, a lot of them are quite similar. So there's only certain levels of gray that we can distinguish between. But something like isoprene, alpha-pinene, sesquiterpene, aromatics, those are almost completely orthogonal to one another. And so we're quite certain about that partition. In terms of whether it is 20% of R2 reacting with NO is the right range, or 50% of R2 reacting with NO, those actually look fairly similar. So that is something we're not going to be able to distinguish. But for sure, the dominant precursor of VOCs we think are quite orthogonal.
think Calvin's hand was up next. Go ahead.
Along those same lines, did the separation of the space sets reveal anything about how much we might need to speciate our monoterpenes and how much there might be cross reaction between the monoterpenes and ice cream products, for example?
Right. Also, great question. So the question is, how well can we separate between different monoterpenes and then also connection or couplings between isoprene and monoterpenes, which two of those products react together somehow and form a ligament that would be in the same size range as the monoterpene or a sesquiterpene when we separate that. So the monoterpenes, it turns out we're surprisingly better at separating this SOA from different monoterpenes than I would have expected. I call it monoterpenes, but actually what works best is alpha-pinene. We've tried beta-pinene, carine, and alpha-pinene. And the regression pulls out the alpha-pinene. And whether or not you believe that, I think it's a fair thing to debate. Because we measure, in our particular way, just composition. And you start with C10 H16, you're going to get C10 H16 or whatever. And we don't really be able to tell that the spectra are unique, it turns out. Maybe not unique enough, so we just lump them all into monoterpenes.
Thank you. We should move on, but let's just thank you all again. And our next speaker is Jessica Haskins, and she's going to talk about wintertime oxidation.
Right, thank you. Today I'm going to be discussing results from the winter campaign. We flew a highly instrumented aircraft in the polluted outflow of the Northeast U.S. during February and March of 2015. We did 13 different flights up and down the East Coast with over half of our flight hours at night. And we particularly flew pretty low in the boundary layer. I am showing an image here of MODIS from the night of Research Flight 8, which is shown here on the flight track. On this flight, it's a case study I'm going to be talking about today, but it really is a great example of how we think about different atypical oxidants during the wintertime. And with a big campaign comes a long co-author list, so I just wanted to point out and thank Felipe, Ben, and Raw for their contributions to this work as well. So when we typically think about oxidants in the atmosphere, we think about the photochemical production of OH from ozone photolysis. And from a radical budget perspective, OH is generally less important during the winter, owing primarily to decreases in water vapor, but also from changes in sunlight and temperature. And this, in turn, makes production from other atypical pathways a little bit more important. And when I say atypical, I'm talking about formaldehyde, which can photolyze to give us 2HO2 radicals, nitrous acid, which can photolyze to give us an OH radical, as well as nitrile chloride, which can photolyze to give us a chlorine radical. And both nitrile chloride and nitrous acid are particularly important in the early morning because they photolyze at longer wavelengths than either formaldehyde or ozone do. And in addition to their primary impacts on the radical budget, both of these have secondary impacts by enhancing both the photolysis of formaldehyde and ozone. So what I'm going to be talking about today is how we have quantified the relevant contributions of each of these pathways during the winter campaign, why it's critical to include these radical precursors in our global modeling, and what to expect if we don't include them or incorrectly estimate them. So I briefly spoke about Research Flight 8, and it was just a fantastic case study to study nocturnal chemistry. What we did is we were following a plume as it aged out from the New York City area, so it spent some time a little northeast of where it's sitting now, and that air blew out and aged over the ocean with essentially no new emissions being injected. It was a solid high pressure system, so we were able to transect the plume and sample it in the Lagrangian pattern as it aged from about 3 a.m. until sunrise the following morning. So what you're seeing here is a time series of nitrile chloride, and this image is actually from the plane at the time that we observed peak CO2 in the entire campaign. So what we're able to do using our measurements from the aircraft is take the concentrations of each of these different radical precursors along with observed photolysis frequencies from the aircraft and calculate the instantaneous radical budget that's coming from each one of those pathways. Now we primarily sampled the layer below that really well-defined boundary layer that you can see in the image, but we were also performing descents so that we could put together a composite vertical profile of the oxidant budget during this time. And so what you can see here is that right around sunrise, around 6:37 a.m., we see photolysis of nitrile chloride and nitrous acid immediately giving rise to large radical concentrations. And only later in the morning do we really see ozone start to take off. And what you see at 10 a.m., this big change is when the plane actually hit point E over here and went much higher than the marine boundary layer to sample and go back to its base. That vertical profile I was talking about looks something like this from only the data collected during our descents on the flight. And you can see that nitrile chloride is the major radical source, but that drops off steeply below about 1,000 meters. And then above that, in line with expectations, ozone photolysis and production of OH in that pathway is more dominant. Now we couldn't stick around all day to see how this budget evolved throughout the day and see how important these early morning sources were. So what we did is we used a box model to simulate the date following our observation of peak CLNO2, which occurred at 6:30 at point D there. And to do that, we used an NCM-based model, which is the framework for 0D atmospheric modeling. It's maintained by Glenn Wolf. As I said, it's an NCM-based model, so it explicitly does thousands of reactions and thousands of species. And we initialize it with our winter data of N2O5, CLNO2, VOCs, etc. We spin it up using prescribed photolysis frequencies from the TUV radiation model. At the end of each spin-up period data, we measure back our observations and then allow free evolution. And we performed 2 simulations, one including chlorine reactions and one not including them. And what we see is that excluding chlorine reactions causes a extremely large underestimate in the integrated daily radical budget the following day. And this is about 2 parts per billion of oxidants, or a factor of 3.75. And you can see this primarily comes from underestimating the primary source of chlorine radicals from CLNO2 photolysis, but it also comes from the secondary impacts that I mentioned earlier. So we take the radical production rate and integrate throughout the day and take the difference between our 2 simulations. We can look at that enhancement in formaldehyde and in ozone. And what we see is nearly 115% increase in formaldehyde concentrations by the end of the day, primarily most of which is happening in the early morning, as well as changes in OH. And I wanted to also see the global impacts of our simulation to put our case study in a regional context. So I'm going to briefly talk about some GSChem simulations that we performed using version 10. We did a standard emissions and chemistry run with updated N2O5 chemistry, and we did a high oxidant run. And what we did for this was we really just multiplied the emissions of formaldehyde up so that their concentrations matched winter observations, and we allowed the photolysis and production of CLNO2. Now, what we see in the model when we include these radical precursor pathways to match their values during the winter campaign are large underestimates in OH, ozone, and they affect things like sulfate, NOx, SOA, and PAN. So, and I should also mention that all of these impacts are underestimated since we are actually underestimating the concentration of CLNO2 in these model runs. So I will leave you with a few key conclusions, and those are that in the fluted boundary layer, there are oxidants available, and CLNO2 is the dominant radical source, but it has impacts beyond just its primary sources that are important to include, and we will need to include and correctly estimate these atypical radical precursors in order to get the oxidant budget right and any of the air quality to the standards that we care about in models. So thank you.
Are there any questions for Jessica? Go ahead, Matt.
So the chloride, do you think that's all sea salt, or is it anthropogenic? So is this an anthropogenic enhancement of chloride from power stations, or is this a natural enhancement of sea salt?
Primarily, specifically for our case study, it's going to be mostly sea salt. We did see some anthropogenic chloride during winter. Ben Lee has a paper about chloride emissions in power plants, so I recommend you do that one. But most of what we're seeing this impact from is from sea salt.
How do you prevent salt?
Sorry?
How do you prevent salt? How do you prevent
I still can't hear your question, I'm sorry.
Are you asking about the source of OH?
Oh, the source of OH. We take our concentrations of ozone and multiply them by our observed photolysis frequencies in the case study to get OH concentrations. And the model has a similar scheme.
Thanks, Jessica. Okay, our next speaker is Jared Brewer, and he's going to talk about the global budget of $3,000 per zone.
Yeah, hi. I'm here to give you the whirlwind tour through the my progress on the global methyl ketone budget. So as to the why we care, MEK, the question here that we're asking is, does MEK play a significant role in the production of HOTS in the upper troposphere? The underlying observation here is the commonality with acetone. So acetone, we know, can be seasonally quite important in that upper troposphere region. MEK, according to some of what's in the literature right now, might be up to as a quarter as abundant as acetone, might last 1 to 2 weeks. If both of those are true, it might actually be very important in the upper troposphere. The question is, are those correct? So to understand that, we're building the budget. This is the map of where I'm going in this talk. All of these steps, these additions to GSChem, but first I want to start out with what does the underlying budget look like. So this is MEK in GSChem version, I said version 12, I guess it's 1102. But 3 sources, of which isoalkanes, Al4, is the most important. 2 sinks to really that matter to OH and photolysis, roughly evenly partitioned. So I'll just jump in then to the changes that I've made. So the first is this updated chemistry. In version 1102, you see that there's this isoprene to MEK branch that was put in originally just as a container for carbonyl compounds, I guess, but isn't supported by any mechanism in the literature. So what I've done here is I've created a separation instead, wherein we still have ALK4 going to MEK, but the isoprene itself is going to this KET container, big ketone. As far as the photolysis goes, this is actually based on some other work that I've done that's about to be published in JGR. This is looking at the temperature dependence of the cross sections of MEK. So what I'm showing you in that first panel on your left is the J value of MEK calculated with both the IUPAC recommendations and with our temperature dependent cross sections. And I'm showing you that here as well. This is the ratio between the two as a function of altitude. In the upper troposphere, these updated cross sections lead to about a 20% decrease in the photolysis rate of MEK. And that's now been added, I've added that into the model as well. Biogenic emission. So GSChem does not currently include, Megan doesn't include a specific emission of MEK. However, we have several observations to suggest that there is one and that it's correlated with isoprene. This is just a specific mechanism that Kaplan et al. Laid out, wherein the in-leaf reduction of MVK leads to the production of MEK. It turns out MVK is poisonous to plant cells. This is a mechanism that's been shown in yeast cells, in cyanobacteria and plant cells. Enone reductase enzyme. So what I've done is I've added a source to the model, 0.5% of the isoprene emission. There's probably a more thorough way to do that, but that's what I've done so far. A dry deposition term. So we know that MEK does dry deposit. It's not included in version 1102. But what I've done is I've done a similar parameterization as what's done for acetone right now, 0.35 centimeter per second, which compares to 0.1 centimeter per second over dry land for acetone. That's in the model at this time. This is what it looks like in various seasons. And then finally, this discussion of an ocean source. So this is data, this is really exciting. This is data from ATOM. You can see how I've been the world for ATOM for this analysis, and I'm showing you the vertical profiles of MEK in summer and winter, ATOM 1 and 2, in South Atlantic, Southern Ocean. Similar vertical profiles can be seen for most of the other ocean bins. And they're robust even if you filter out polluted air masses. You can still see this vertical profile. So this is another paper I'm working on that suggests that there is actually an oceanic source for MEK. But I'm going to talk about what that looks like in GSChem right now. So we only have one observation that I'm aware of MEK in ocean water. If anybody knows more, please tell me. This is an observation from a coral reef off the Australian coast. Very, very high concentrations, 102 to 119 nanomolar. Similar concentrations seen for acetone in that same water, which would also be very high acetone concentrations. Two different ways that we've dealt with OVOCs in the ocean in the past. We have an acetone-like example where you have the whole globe as a 20 nanomolar ocean. Turns out that when you set it at 20 nanomolar, that source is so large that I'm not even going to show it here today. Then we also have this acetaldehyde-like parameterization where it's linked to phytoplankton. And that's what I've moved forward with. So the max in this is the observation that we've got. So how are we doing? This is the comparison to the ATOM observations. What I'm showing you on the x-axis is the log of the ratio modeled to observed. So if that number is positive, that means the model is overestimating MEK relative to the observations by 1 or 2 orders of magnitude. It's negative, it's underestimating, and that solid line is the 1-to-1. And what I'm showing you with this plot is just without our ocean source, we're biased low over a lot of these regions. Yeah, in the ocean, we're then biased high. So probably overtuning the ocean a little bit. But the underlying point here is that we need this ocean source in order to come close. So I wanted to close with this sort of handmade graphic, talking about going back to that original question of does anything matter in the upper troposphere for observation? And I started this by saying, well, if it's, okay, so if that ratio is 4-to-1 acetone to MEK, then maybe it's important. And that's, so the literature, past literature, I'm showing you ranges, these are ranges by season. Past literature is saying between 4 and 13 times as much acetone as MEK. ATOM does not agree with that, notably. In the upper troposphere, more like 40 to 80. If you do this updated geochem with photolysis, chemistry, biogenic emission, and dry deposition, we end up completely after lunch, 260 to 300 times as much acetone as MEK. Do all that, and then you add in this ocean source, we're back down at this 4 to 8 range. Again, probably an overtuned notion, some more work to do, refining that parameterization. But this is where I'm going, and hopefully I'll be able to calculate the lifetimes soon and give you an answer ultimately to whether or not it matters. So I'm happy to take your questions right now.
Questions from Jared? Oh, Daniel, go ahead.
Would your methyl ethyl ketone source from the ocean, could it be secondary so that you would have?
So you're releasing some precursor and then it's immediately being turned into anything?
I know, yeah, because we talk a lot about oxygenated VOCs being generated over the ocean, the secondary products.
Or if it's being produced like in the surface layer and then being, I don't know the answer, but yeah, that's an interesting question.
Sorry.
Have you looked at all at adjusting the yields of MEK from the R402 as it comes from forward?
So adjusting the yields, I've looked at adjusting the rates a little bit to match what Wendy Golov has in RAPID 2. I haven't really looked at adjusting the yields, though. That's a good question.
I think there's a sort of
interesting. Okay, I'd love to talk to you more about that.
Thank you. Yeah. Our next speaker is Chris Holmes, and he's going to talk to us about the role of clouds in the tropospheric Knox cycle.
Thank you. I'm going to tell you about a way in which we can improve our means of simulating cloud chemistry. I'm going to give you an example based on Knox chemistry, but really what I'm talking about, the methods I'm introducing are relevant to really any cloud chemistry in geochem. So this began as a graduate course project, and that's the FSU collaborators here, and Tim Bertram and Viral Shah were also very helpful in this work. So I want to remind you that N2O5 hydrolysis on aerosol is an important sink of NOx. This is based on a lot of field studies and modeling studies over many, many decades. And the chemistry is that N2O5 is taken up into an aerosol, converted to nitric acid or nitrile chloride. And the rate of that depends on the surface area, particle size, diffusion, and a reactive uptake gamma, which summarizes all of the internal chemistry at the aerosol surface. Now, we have standard formulas first put out by Steve Schwartz that express the rate of these as a function of those aerosol properties. And a lot of laboratory work has defined what these gamma rates are, and for aerosols, it's complicated. It depends on aerosol composition, but it falls into a wide range, up to about 0.02. For water and ice, which are relevant for clouds, the range is much smaller, 0.02 to 0.03. And this comes from IUPAC and JPL values. So based on that, our current understanding is that aerosols account for 20 to 35% of global NOx sink, and it reduces global OH and ozone by about 1 to 4%. Now this is all based on aerosols, but what about clouds? Well, clouds have about 1 million times greater surface area than aerosols. Their impact, however, is mitigated by the timescales for cycling in and out of clouds. That takes about a day. So past literature has suggested that clouds have a very small impact on N2O5, but all of those past studies assumed that the gamma on aerosols was way too big, much larger than we now know is realistic. So past studies overestimate the impact of clouds, and so I'm going to revisit, the past studies overestimate the impact of aerosols. Now that we have more realistic aerosols, I'm going to go back and ask, are clouds important? We have to come to the basic issue of how do we resolve cloud chemistry in a model that does not resolve individual clouds. So we have a cloudy fraction in which the loss of N2O5 is very fast, about a 30-second lifetime in the cloud. But much of the grid cell is going to be clear air, and the lifetime is going to be essentially infinite. What is the average lifetime of N2O5 in this environment? Now, it's been addressed in the past in various very unsatisfactory ways. One is to mix the cloud through the entire grid cell. That results in a loss that's way too fast. Another is to assume that there's a hard division between the cloudy fraction and the clear fraction in each model time step. That's unphysical. So I suggest a solution in which we just impose the rates of entrainment and detrainment as an additional physical mixing process. And within the cloud, we use our standard Schwartz equation. And with this and some algebra, you can derive a single first-order loss rate, integrating the in-cloud loss rates, the cloud fraction, and the entrainment. And this is the equation that you get. Now, the details aren't that important, but those of you with eagle eyes may recognize that the two right-hand terms are the Schwartz equation for uptake in an aerosol. The left term is an entrainment. So entrainment acts in series with the surface uptake in a cloud. And when you put in realistic values, you get about a 10-hour lifetime for N2O5. So realistically, we have a slow decay of N2O5, whereas if you do those other two inaccurate methods, you get very fast loss or something that depends a lot on your chemical time steps. This is what all other models, including GeosChem, are doing for cloud chemistry, to my knowledge. So the advantage of this entrainment limited uptake is that it's now physically realistic. It's analogous to the Schwartz equation, in fact, it's actually a generalization of it. It's simple and fast, and it's applicable to any irreversible chemical reaction inside clouds. Again, I'm just giving an example for N2O5. But I'll show you the results of how this impacts oxidants in GeosChem. So we updated the gamma values for all NOY species. We used the Bertram and Thornton parameterization for sulfate nitrate ammonium. And of course, we implemented entrainment limited uptake. These are the loss frequencies for N2O5. And most importantly, you see that the loss is fastest where the cloud fractions are high, not necessarily where clouds have a lot of surface area, which would be more in the lower troposphere. For the NOx budget, this figure, the black line there, read off the right axis. So production of nitric acid is fastest in the northern mid-latitudes, where we have a lot of emissions. Overall, the colors indicate that homogeneous gas phase oxidation is responsible for most nitric acid production. And aerosol uptake provides about 30% of the NOx loss in the northern hemisphere mid-latitudes. That's what past literature has found, essentially. The new aspect here is that clouds actually provide 25% of the NOx loss at high latitudes in both hemispheres. Average globally, that means that clouds are responsible for about 5% of NOx losses, with the additional important caveat, which I'm not going to talk about further, which is adding in the clouds actually makes us less sensitive to aerosol chemistry, because there's a competition between clouds and aerosols for that N2O5. So adding in the clouds makes us less sensitive to the aerosol surface area, less sensitive to the aerosol gamma. Now, of course, we want to see how this compares with observations, and the message here is that it doesn't break anything. this cloud chemistry does not have a big impact relative to the natural environmental variability. And I'm showing just two examples of NOx profiles and ozone profiles. And the colored dashed lines indicate the different versions of the model that I talked about here. There's very little change. In addition, Becky Alexander tells me that we have some improvements in the nitrate bias and in the oxygen isotopes, although that's mostly due to the gamma values, not necessarily cloud impacts. So I think we should include this. Cloud chemistry, the chemistry is clear, we know what's happening. And I will end by pointing out a few takeaway messages here. First off, cloud impacts are important for NOx. Up to a quarter of NOx loss, 5% of global NOx loss, and it's been overlooked because early studies used an incorrect gamma value. I finally want to end by mentioning where else this is important. So just a list of other places where cloud chemistry is important. SO2 oxidation, halogen cycling, HO2 uptake, aerosol processing of composition and number concentration, aqueous mercury reduction. These are all things where this approach should be applied. And I would like to work with some of you on doing that and seeing what its impacts are. Thank you.
We can't take all your questions, but let's start with Brad.
What do you do with the nitric acid that you use? Is there something clever that we can do, or do we just release it into the grid box?
So I have not changed the assumption that we have well-mixed grid boxes. I'm just modifying chemical production loss rates. But certainly, subgrid scale issues and subgrid scale gradients in composition are something that we neglect in all cases. So I have not changed that assumption of mixing in most respects.
Jeff?
You could add positions to that list. And where did you get the entrainment rates for the large scale clouds? That field probably depends a lot on where you are in the atmosphere.
Yep, so that's where I think there's a big opportunity for improving this. Right now, I have used a representative 1 hour timescale, which is similar to what is observed for many cloud types, but I think there are some opportunities for further improving that.
And just one more from Jenny.
So we currently underestimate the NOx. I'm just wondering, you said that you've added now 20-25% NOx loss from cloud chemistry. Is that taken away from the loss pathway, or do you actually have?
It would be more. I have not quantified exactly how much more. Overall, nitrate production in the high latitudes is about 2% higher with this, so small impacts. I'm not claiming that this would fix every aspect of NOx chemistry in the model by any stretch.
It's evoked a lot of discussion, but I encourage you to meet with Chris during one of the coffee breaks or lunchtime. Our next speaker is Kelvin Bates, and he's going to talk about redefining odd oxygen.
All right, thanks, Eloise, and good morning, everyone. Good to see so many familiar and new faces here at our little reunion. I'm Kelvin Bates. I'm a postdoc here with Danielle. Those of you who know me are probably surprised not to see the word isoprene up here. Don't worry, I still work on that and would love to talk to you about isoprene or any other gas-phase oxidation mechanism you might be curious about. But I thought I'd spend my short time with you today talking about a little side project we've been doing, looking at how we define odd oxygen in geochem and what that means for tropospheric ozone budgets in general. So the question that we are getting at here really is, where does tropospheric ozone come from? And through that, what controls its budget? Obviously, we care about tropospheric ozone for a number of reasons, perhaps more than any other thing in most chemical transport models. It's kind of the basis on which we compare a lot of our models to observations and to each other. And we spend a lot of time, much as we might not like to admit it, sometimes tuning the model to try to get those observations and simulations to match. And so we can do pretty well on the burden of ozone in the troposphere, but that doesn't necessarily mean that we are getting ozone right for the right reasons. And that's kind of shown by the broad spread in budget terms across models. And so the question is, how can we better constrain getting ozone right for the right reasons by better understanding its sources and sinks and their relative importance? So to go back to that question, where tropospheric ozone comes from, you can probably all answer this with something out of Atmospheric Chemistry 101. You'd say something along the lines of 10% comes from the stratosphere, 90% comes from the reactions of NO with peroxide radicals, and you would be broadly correct. But you could also have said, alternatively, that 99% of it comes from the reaction of atomic oxygen with molecular oxygen, And you would also have been correct, just not at all useful. And that's because most of our atomic oxygen, 99% of it approximately, comes from the photolysis of ozone. So this is a null cycle that is extremely efficient in the troposphere, but it doesn't actually do anything to the burden or budget of ozone. And so we'd like to ignore it, and we do that by combining ozone and atomic oxygen into what we call odd oxygen, uncreatively. And by looking at the budget of odd oxygen now and its sources and sinks, we can ignore the rapid cycling that takes place within that family. And we can extend this to all the other species with which ozone readily cycles, which gets more and more complicated as we add more and more species to our chemical mechanisms. But we've arrived at what we think is a reasonable definition for odd oxygen and for defining our ozone budgets, right? Maybe not right. That is because the main sink of odd oxygen in models right now is the reaction of O singlet D with water to produce OH, all well and good. But most of that OH will go on to react with CO or VOCs and produce HO2, and much of that HO2 will go on to react with NO to reproduce your odd oxygen, your ozone. And so what we have here is effectively just another cycle that I could have just included with that odd oxygen cycling that I was showing you before. And in fact, because that HO2 and NO reaction produces OH, you can get some effectively amplification of this cycle down here, and your O singlet D and water reaction becomes not a sink, but potentially a source of additional ozone if you can get this running efficiently. So a more theoretically sound version of odd oxygen might incorporate this cycle within the family so as to look at the external sources and sinks, which is effectively what we've done here. And we do it by making a new little odd oxygen family on the side that we're calling OC in this case. You can think of this just as you would many of the other, and then we look at the sources and sinks of the broader family rather than just OX. You can think of this just as you would some of the other families that we know and love. So for example, the nitrogen oxide family, we usually think of as NOx being the rapid cycling NO and NO2, and then NOZ is the broader reservoir species that are longer lived and that take something external usually, like light or heat, to be converted back into your rapid cycling NOx. And we are doing just the same thing here with our odd oxygen, in that OX is the family I introduced to you before of the rapid cycling species. And then OZ is this additional cycle through OH and HO2, and it requires something external, in this case NO, to be converted back to OX. And then OY is just the combination of the two, as with any of the other families. It turns out that HOX and HOZ cycle on timescales that are relevant to this as well, along with some halogens playing in here. So we have to modify this a little bit. We have to put that 0.5 out there just to get the stoichiometry to balance, but it works, trust me. So to look at this a little more schematically, I know this is busy, but the main thing up here is what I've already showed you, that OX and OZ cycle through those reactions that we have looked at so much. This is showing the flux through all of these pathways in an annual simulation in GeoSchem. And what you can see immediately is that some of the largest fluxes are through this cycling right here, which is goes to show the importance of including this cycle within our family. And the other thing I want to point out on this is that we've now related odd oxygen back to effectively more stable sources and sinks in the troposphere. So your only sources now of odd oxygen external to this box are stratospheric influx and the photolysis of stable carbonyls. And your only sinks now are deposition and conversion to true terminal sinks in the form of your larger oxygen reservoirs effectively in the troposphere, and those are O2 and water. So you might be asking at this point, why exactly do we care? Isn't this just semantic, really? To some extent it is, but I would argue that semantics matter. But also this does kind of redefine how we look at the relative importance of various processes like the sources and sinks here. So for example, I told you earlier that the stratosphere is approximately 10%. And I got that just from comparing that 500, this 4,500 down here. But in this new framework, if we consider that some of that 4,500 down in this pathway came through OZ, it came through that O singlet D, and it originally came from the stratosphere, now we can account for that. We can do so by grabbing a number of equations from this framework or by tagging ozone in GeoSchem, and it keeps its stratospheric tag when it goes through this cycling. And when we do that and follow it around, we can see that in this new OY framework, it appears that 30% of surface ozone is stratospheric in origin, whereas an old OX framework would have told you that 15% with stratospheric in origin. So that's a fairly large difference. Another way of just looking at that similarly is to say that we've changed the effective lifetime of ozone. So whereas this would have been a sink of ozone in the past, we now consider it to be staying within the family, it isn't lost, and therefore you've effectively extended your lifetime to approximately 2 months within the OY family, where it would have been about 3 weeks in the OX family. So I'm just going to leave these up. I've said them all before. This is only a tiny piece of this puzzle. We've submitted a paper on this, so I'd be happy to take any questions now or throughout the week. Thank you.
Any questions for Calvin? Oh, sorry.
So I think it's interesting. I'm not going to ask this question. So I understand what you're doing about the budgets.
Yes.
But are you really answering the question where is stratospheric ozone coming from? Is that? I mean, you're not really saying that if I turn off stratospheric chemistry, that I'll still get good. Or are you saying exactly that?
I'm saying in part that. I guess I wouldn't do it by turning off tropospheric chemistry, but if you turn off stratospheric input, you will not just get a 10% reduction in, as the past budget would have said, you will get a much larger reduction. There are a number of reasons for that. Part of it is because your cycling is more efficient up high. But I think this is also a good way of looking at that and of reframing how we view the importance of that source. You're right that this doesn't effectively change any of the chemistry, right? But I think it is still important to be looking at where we say these things come from.
So, does this mean, I'm not sure I follow this, but does this mean that atmospheric chemistry also is more sensitive to changes in stratosphere circulation and ST?
Then a simple previous budget analysis would have said yes, although you just run some perturbation experiments, it'll give you the same answer either way. But I think this is a better way of framing how we look at that perturbation experiment and what we might expect to get out of it. And yes, the answer, I guess, when you look at it this way, is effectively the stratosphere, changes in the stratospheric influx of ozone be more important than we might have previously thought.
We should move on. Thanks, Calvin. Our next speaker is Irene Dudusi, and she's going to be talking about developing the adjoint of the GeoScan VCA.
Great, thank you. Hi everyone. So I'm going to talk a little bit about the development of the adjoint of the GeoScan Unified Stratospheric, Tropospheric Stratospheric Chemistry Exchange, or UCX as it's known. So there's 3 main things I'm going to talk about. First, we're going to talk a little bit about why we're bothered doing this. Secondly, we're going to present the model development and the evaluation. And thirdly, I'm going to just give you 2 quick sensitivity examples or application examples to demonstrate the potential of this new development. So the main reason why we're doing this is because there's renewed interest in stratospheric ozone, but there is high uncertainty in the stratospheric perturbations. And what I mean by that, there's a lot of interest and a lot of, I guess in the past decade or half a decade, potential introduction, for example, supersonic aircraft that would be flying at about 50,000 feet. So at the lower or within the ozone layer, there's an increasing number of rocket launches, which are creating emissions in very clean levels of the atmosphere. There's recent interest in industrial chemicals that are not currently covered by the Montreal Protocol that could be affecting stratospheric ozone. And at the same time, stratospheric ozone is likely, is affected by changes in the meteorology. So the common underlying theme of all these potential perturbations that might affect stratospheric ozone is that there's high uncertainty. We don't really know, for example, for aircraft, if they'll be flying, how many they'll be flying, what altitude they'll be flying, and so on. And this is really what motivates the development of the adjoint. So given the receptor-oriented sensitivities, the nature of the sensitivities, of adjoint sensitivities, in an individual evaluation of an objective function, we can effectively calculate how any perturbation in the species, space, and time domain affects some aggregate quantity of interest, and in this case, for example, ozone blast. And in this case, we can sort of use the sensitivities, take advantage of the nature of the sensitivities to examine this uncertainty in the perturbations. And the geoschema joint so far has been mostly tropospheric focused, so the goal of this was to bring into the geoschema joint the UCX capabilities. Now, for those unfamiliar with the adjoint, the adjoint model consists of two parts. One part is a geoschem model inside it, so-called usually referred as the forward model. And then there's an auxiliary set of equations, the differentiated counterpart of that forward model, which comes with that, and that's the one that calculates the sensitivity. So when we set out to develop the adjoint of the UCX, there's two steps that we need to take. Step number A being updating the model, the geoschem forward model that's within the adjoint. And step number B being to create the differentiated version of those forward model updates. And I'm going to briefly talk about those two steps. So step A, updating the forward model. So we brought in the updates, the UCX updates from Seb Easton, the main of which is that the chemistry is now extended to 50 kilometers. We've added 37 new traces and about 250 or 260 chemical reactions, as well as updated the photolysis scheme to FastJX. And the way we made sure that it works is we've looked at the ozone for a long-term 5-year simulation, similarly to how it was done when validating or when evaluating the UCX development. And what you're looking at here is just the forward model. This is just the normal geoschem with UCX on. In the middle, we have the forward model as it was before our additions. And then at the bottom, we have the forward model of column ozone, zone only column ozone, that after we've done the UCX changes. And so basically, the aim is to make sure that the bottom one matches the top one, which it does within about a 3% green. So updating the forward model is step number 1. Step number 2 is creating the differentiated counterpart of those updates. That was done with a discrete adjoint formulation to ensure algorithmic consistency between the two. It was a combination of manually derived and automatically differentiated models. And the evaluation, similar to how it's usually done, is we compare finite difference sensitivities with the adjoint sensitivities. And we did that at a tropospheric altitude to make sure we haven't messed up the tropospheric capabilities of the model, and then also at a stratospheric altitude to ensure that what we've added to the stratosphere is appropriate. So some two quick sensitivity applications. The first one, we're looking at sensitivities of oxygen at the stratospheric altitude with respect to chlorine perturbations and with respect to NOx perturbations for a short-term simulation of just 2 weeks. So whatever we're looking at is only effects of local chemistry. There's no actual transport coupling effects given the short time. And looking at the left plot, we're looking at the sensitivity of oxychlorine, and which highlights the ozone hole layer. Let's say that this is for September, which is the Antarctic spring, which is when the ozone hole forms. And then secondly, on the right-hand side, we're looking at sensitivity with respect to NOx, and we are observing the negative sensitivity right within the core of the vortex, but the sensitivity switches sign actually as we go towards the edge of the vortex, which is tied, which is one chemical explanation that why the ozone hole is contained on those in that region. And then secondly, this is just looking at OX at different altitude bands. On the left-hand side, we're looking at OX between 10 and 20 kilometers, and on the right-hand side, we're looking at OX between 20 and 30 kilometers, and in particular, how the sensitivity of NOx to ozone varies. And we see some switching of the sensitivity sign as expected when the two effects of tropospheric ozone formation versus stratospheric ozone diffusion balance out. So finally, this is about the development of the geoschem UCX adjoint. I'm happy to talk more about it. You can find me around. With the main reason that motivates us is the uncertainty in the perturbations. All UCX capabilities are implemented and the short-term sensitivities are evaluated. Long-term sensitivities, however, are currently under testing, mostly due to challenges with transport and chemistry instabilities. So, thank you.
Irene.
The PSC formation process. Does the adjoint have a difficulty with this because it's on an on-off kind of thing?
Hey, so the reason that this chemical instabilities that we are facing, we're not actually sure where they originate from, and this is one of the reasons they could be originating from. So this is something that we're looking into right now.
I latched onto the one point that you had in your introduction about rockets and the impact on the stratosphere. Do they have a large impact on the stratosphere? I suppose I'm the line of the loop.
I don't actually know the answer to that question. Something that motivated is we haven't looked into it. But they might. I mean, they're increasing, and we don't really know actually what plume of rockets are very poorly characterized. So.
If there are no more questions for Irene, next we have the chaos of the poster introductions. So if you are introducing your poster, please come up now. And you're going to stand sort of behind this exit/entrance area. When your poster comes up, head to the podium, give your 30-second spiel, and then head straight off stage.
It's actually pretty good.
We're ready to go.
Hello, my name is Ben Brownsteiner, and I'll be presenting a poster on Furon oxidation
Sorry, if you
chemistry.
could just be quiet for the poster introductions. Thank you.
On Furon oxidation chemistry, which is very complicated. We're trying to depict both simple and complex mechanisms to see how much the complexity matters. And we're developing the mechanism by also running some chamber oxidation experiments to kind of constrain all of the branches. And sometimes science makes me sad, but usually it makes me happy. But
Hi, I'm Will Swanson. I've been looking at reactive bromine over the Arctic Ocean. I'm comparing those to integrated vertical column densities in geochem with blowing snow. We were able to replicate the ozone events here in spring 2015, but we're not able to replicate the full peak of observed reactive bromine. So come on poster and talk to you about reactive bromine.
So I didn't have time to make an extra slide, so now you've all seen my poster. Congratulations. Believe it or not, some people do use other models. And one of the things that I'm doing, so one thing I make sure they do is benchmarking. So in this case, I'm comparing a bunch of work that's being done in the EPA using CMAC at the hemispheric models, the hemispheric scale, to geochem to understand where the strengths and weaknesses of hemispheric CMAC model lie, to understand the policy implications for those strengths. There's a lot that won't fit on this poster, and I'd like to talk about all of it with you. Oh, and because I won't get to talk to each of you individually, Shannon Copeland says hi to all of you.
Hi, my name is Jason Ducker. I'm working under Dr. Christopher Holmes at Florida State University. We're looking into photolysis rates and creating a new data set of photolysis rates globally. So previous models have had global averages for photolysis rates differing by at least a factor of 3, with even larger differences regionally. Model assumptions such as cloud overlap is also a main issue that has not been currently resolved amongst chemistry models. And last 10 years, NASA A-train satellites have been continuously around the globe. So we are now integrating NASA A-train satellites, which measures clouds, aerosols, as well as some meteorology gases, and we're going to use the FastJ algorithm incorporated with NASA A-train measurements to produce a photolysis data set across the globe and use geochem and aircraft observations as a basis for evaluating this product. So come by my poster at 8:10 and we'll discuss more about it.
Hi everyone, I'm Hannah Horowitz. I'm going to be presenting some work about marine cloud brightening, which is a potential geoengineering technique that's being considered that would emit additional sea spray into the atmosphere to offset some of the warming from greenhouse gases through clouds and the direct aerosol effect. But all the previous work trying to estimate what the effects of this additional sea salt would be and how much you would need to decrease temperature have not considered the impacts on atmospheric chemistry. So what does this mean for oxidant budgets? Are there any feedbacks with greenhouse gases or potential co-benefits with air quality? To find out, come to our poster at A11. Thank you.
Hi, I'm Jason from MIT. So understanding global age is very important for projection air quality and climate. So here I'm using surface network and satellite observation, the HCFCs and HFCs as method curve for alternatives to constrain global age concentration and distribution. So we found strong variation in hemispheric variation over past 2 decades. So if you want to know more, consider proceed.
So we compare the impact of running geoscam version 12 at 2 different resolution at 105 on simulating the tropospheric ozone. So we see the result shows that there are large changes in stratosphere and troposphere exchange across the resolution, and on tropospheric ozone burning changes are less than 3%, but there are largely no changes. If you are interested, this will come to A13. Thank you.
Nowadays, the instrumentation really has a superpower, measuring everything or nearly everything in the atmosphere for those atmosphere compositions. But how many do that matters, and how many should we really include in the model? So this poster is really talking about the data we collect during weekend campaign, which was led by Emily Fisher, showing the mass spectrum we measured for those volatile organic compound. Basically, see each peak representing one species or multiple species. But those highlighted red bars are those we represent in the geoscan. So this poster really trying to have the discussion with you to think about what kind of VOC we should be including in the fire environment or basically in any other urban or any other environment. Looking forward to see you there.
Hello everybody, I'm Jamie Kelly, and my poster is about polycyclic aromatic hydrocarbons, which are potentially carcinogenic and they bioaccumulate in animals. And the question we are answering here is how important is the gas to particle partitioning scheme on PAH life cycle? The answer is quite sensitive. So the global PAH burdens vary by, well, they change by -70% to +41%, depending on that gas to particle partitioning scheme. So if you're interested in this, thank you.
Hi, I'm Dusan from GU Bordeaux and NCAR. We developed a new parameterization, especially for iPox-SOA, which successfully captures the iPox-SOA by explicit full chemistry. One of the main advantages is that our new parameterization successfully captures the response to emission changes, especially for NOx and SO2 emissions. And also I included several side projects like organic cooling effect or also pH on SOA formation, also global health effects. So if you are interested in, please stop by my poster.
Hi everyone, I'm Yokchun Chen from University of Washington. So it's not news that GEOs can have some problems simulating nitrate amounts sometimes. We often don't get the right amounts of nitrate, and some isotope measurements also show that we get the wrong nitrate in the wrong way. So we have got some thoughts about it, and we are developing some heterogeneous chemistry to help reducing the model bias. So if you care about nitrate formations or the case in Beijing or in northern China or about like isotopes measurements, just jump by the poster. Thanks. Looking forward to it.
Hi everyone, I'm Hong from UK. So basic emissions are increasingly important compared to mobile sources in terms of VOC emissions. However, basic emissions are likely underestimated by factors of 2 to 3 based on a science paper published last year. So in this work, we did a series of simulations using different basic emissions with different SOA yields. So if you are interested in how this will impact SOA simulation in urban areas, please stop by 18. Thank you.
Hi, my name is Shoma Timanochi, and my research centers around ground-based FDR spectrometer, which we did at the University of Toronto in downtown Toronto, Canada. And this spectrometer pictured here can make column profile measurements of ozone, CO, methane, ethane, etc. And today I'll present screening emissions estimates made with the observations with supplementary analysis done on the geoscan impact CO simulation. Please come by.
I'm starting off from first page. My topic is about tropospheric ozone change over Southeast Asia. Both satellite observation and geoscan model show significant tropospheric over Southeast Asia. And so our question is, what drives the tropospheric ozone change in this region? Now we find that global anthropogenic emissions contribute the most. Welcome to my poster. Thank you.
Hello everyone, my name is Oren Zhang and I'm from US. This work investigates the potential impact of authority on the production of particular matter and the order in case of emission limit policy. Regional model CAM and the VPS was adopted for simulation. If you are interested in the related topics, please don't miss it. Thank you.
Okay, I would like to thank all the presenters from this morning's session. We're now going to break for lunch. So we'll reconvene in an hour and a half. There are lots of lunch options here. You can ask for locals, but there's food trucks, cafeterias, all